Hello there, and welcome to Science for Sleep, where curiosity drifts softly through the quiet corners of the universe, and science takes its time to settle like dust in sunlight. Tonight, I'd like to invite you somewhere familiar yet rarely seen. Not to the planets themselves, not to the glowing orbits of Venus or the storms of Jupiter, but to the vast, unseen space between them. That quiet, endless distance where almost nothing happens, and yet everything that does holds the shape of our solar system together. Before we begin, I wonder where you're listening from tonight. Maybe you're beneath a sky just starting to darken. Maybe you can see a planet or two. Tiny, bright points that look still, but are really moving through space at unimaginable speeds. Perhaps you're winding down after a long day, letting the noise of the world fade as you reach for a bit of stillness. If you find this little journey soothing, if it helps you rest or simply gives your thoughts a calm place to wander, it would mean a lot if you liked the video or subscribed. It helps this quiet corner of science find more listeners who need a bit of peace too. Now, if you're comfortable, settle in. Slow your breathing. You don't need to focus too hard. Just let the words move at their own pace. Because between every planet, beyond the orbits we trace and the maps we draw, lies a vastness that almost defies imagination. And that's where we're heading tonight. When people picture the solar system, they often see it as a neat diagram, circles within circles, the sun in the middle, each planet spaced politely in its lane. It looks compact, orderly, like something you could almost hold in your hands. But those diagrams are lies of necessity. The real distances are so great that if Earth were a small marble sitting in the middle of a football field, the Moon would be about the size of a pea hovering 30 centimetres away, and Mars would be nearly 2 kilometres down the road. The nearest planet is so far that even light, the fastest thing we know, takes minutes to cross the gap. That's not just empty space. That's a kind of silence most of us can't imagine. Yet calling it empty isn't quite right. There are no walls in space, no true void that's completely nothing. The space between planets is filled with traces of matter and energy, whispers of what the sun breathes out, what the planets shed, what comets leave behind. In the same way, air fills every room even when you can't see it. The solar system is filled with a diffuse, invisible presence, a thin soup of particles, magnetic fields, light and dust. It's just that it's so thin that a single cubic meter might hold only a few atoms. For comparison, the air around you right now contains roughly 1 trillion of them. So what does it mean to say between planets? It's not a gap with walls. There's no clear start and stop where one planet's domain ends and the next begins. Instead, the space between worlds is more like an ocean, continuous and connected, with each planet moving through the same sea, leaving ripples behind. The sun, sitting at the centre, is constantly stirring that ocean, sending out a wind that never stops blowing. It's a wind made of charged particles, protons, electrons, bits of atoms stripped bare by the sun's heat. This solar wind travels in all directions at hundreds of kilometres per second, shaping the entire solar system. It's invisible, but it's real enough to push comet tails away from the sun and carve out vast magnetic boundaries around planets. If we could stand between worlds, which of course we can't, because there's no ground, no up or down, what would we see? Not much at first. The sun would hang in the distance, a dazzling sphere far brighter than any star. Around it, tiny dots of light, each a planet or moon, would move slowly across the darkness. Between them, nothing obvious. No clouds, no drifting rocks, no glowing mist. Just blackness so deep that it seems like an absence. But through that darkness, radiation and particles are constantly moving. Light from the sun, travelling outward in all directions. High-energy particles from distant stars rushing in. Dust grains from shattered comets glinting faintly when they catch the light. Spacecraft that have ventured outward, like Voyager and Pioneer, have crossed billions of kilometres through this invisible environment. The The instruments on board detect it not through sight but through faint clicks and hums, the rhythm of charged particles hitting sensors, the magnetic fields changing around them, the density of plasma rising and falling as they move farther from the sun. Through those signals, we've come to understand that the space between planets is not dead. It's a dynamic, restless medium that breathes with the pulse of the sun. Every second, the sun releases about 1 million tons of material into space. It's not as dramatic as it sounds, considering how vast the sun is. This outflow creates the heliosphere, a giant bubble that encloses the entire solar system and protects it from much of the harsher radiation that fills interstellar space. Inside this bubble, the solar wind dominates. It pushes outward against the interstellar medium, forming a kind of cosmic frontier far beyond the orbits of the outer planets. Closer in, that same wind defines everything from the shape of planetary magnetic fields to the behaviour of dust near the sun. But even with all that movement, the scale of distance remains humbling. Between Earth and Mars at their closest, they're about 55 million kilometres. If you could travel at the speed of a passenger jet, around 900 kilometres an hour, it would take over 7 years to get there. Between Jupiter and Saturn, the space is so wide that you could fit more than 1,000 Earths lined up side by side. These distances aren't just numbers. They define a kind of cosmic loneliness. Planets are like isolated islands, connected only by light and the invisible tides of gravity. That's why every mission we send feels so momentous. Each spacecraft is a fragile, human-made island, hopping from one shore to another through an ocean so vast and so thin that it almost doesn't feel real. And yet, everything we know about the planets, their atmospheres, their moons, their weather, comes from signals that travelled across that ocean, carrying bits of data encoded in light or radio waves. The space between worlds is the medium that allows knowledge itself to flow. It's easy to imagine that if you were floating between planets, you'd feel nothing. But space is never truly still. The particles of the solar wind would pass through you in unimaginable numbers, though each carries so little energy that you wouldn't notice. Cosmic rays from distant galaxies would zip by occasionally, rare but powerful enough to leave traces in detectors or even in the film of old cameras carried by astronauts. And every so often, a tiny dust grain no larger than a grain of sand might collide with your ship at tens of thousands of kilometers per hour, releasing a burst of plasma on impact. In a place where almost nothing happens, even the smallest events are dramatic. Temperature, too, becomes a strange concept out here. Without air to carry heat, there's no single value that describes how hot or cold it is. In sunlight, surfaces can heat to hundreds of degrees. In shadow, they plunge to hundreds below zero. The interplanetary medium itself, despite being near vacuum, has an effective temperature of millions of degrees if you measure the energy of its particles. But there are so few of them that they couldn't warm even the thinnest layer of skin. Space doesn't feel hot or cold the way air or water does. It feels like nothing at all. Still, the nothingness has texture. It carries the sun's magnetism, woven into the solar wind. These magnetic fields twist and fold as they move outward, shaped by the sun's rotation, forming a vast spiral pattern that extends across the solar system. Planets, with magnetic fields of their own, like Earth and Jupiter, interact with this flow, creating bow shocks and magnetospheres that deflect the charged particles. This interaction is invisible, yet it's responsible for things we can see, like the auroras that dance near Earth's poles or the bursts of radiation detected near Jupiter's moons. It's a strange kind of beauty, the kind that exists entirely in forces rather than forms. Between planets, beauty isn't something you can photograph easily. It's not colour or texture, but motion and influence. The way energy spreads, the way space flexes slightly under the pull of gravity. Even light behaves differently here. Close to the sun, it's fierce and brilliant, bouncing off everything with sharp precision. Farther out, it becomes softer, more diffuse, a dim lantern glowing through dust. By the time it reaches the realm of the outer planets, it's barely enough to see by. The sun becomes just another bright star in the dark. And still, that faint light travels. It touches every grain of dust, every piece of rock, every frozen world, carrying warmth and information. Some of it reflects, some is absorbed, some scattered into directions that will never meet another eye. Light is the messenger that connects the solar system, the only thing that truly crosses the emptiness. Without it, there would be no way to know anything at all about what lies between worlds. If you could somehow listen to the solar system the way spacecraft do, translating electromagnetic waves into sound, you wouldn't hear silence. You'd hear a faint hiss, a low hum, occasional bursts and clicks. That's the solar wind interacting with magnetic fields, plasma waves resonating through the interplanetary medium. Instruments aboard the Voyager probes have recorded these sounds. They're eerie, not musical, but unmistakably alive. In them, you can sense the pulse of the sun, the rhythm of charged particles moving through space. That hum is constant. Even in the darkest corners between planets, something is always moving. The distances might stretch beyond comprehension, but there's no pause. Every second, radiation from the sun and from the universe beyond washes through the solar system. Microscopic particles drift like pollen, invisible but persistent. Gravity tugs on everything, maintaining its endless conversation. In that sense, the space between planets isn't empty. It's the medium through which everything communicates. The next time you see a picture of the solar system, you might notice how clean it looks. The black background, the crisp orbits, the perfect spacing. Real space isn't like that. It's filled with movement, with faint matter that catches light in subtle ways. When sunlight hits the dust scattered through the inner solar system, it creates a faint glow known as zodiacal light, a soft cone visible from Earth just before dawn or after dusk, if you're far from city lights. That glow is the reflection of countless dust grains, slowly spiraling inward under the influence of gravity and sunlight. Even the emptiest places shimmer when you know how to look. And then there's perspective. When we think about between planets, we imagine a gap that we might one day cross, as if the solar system were a neighborhood and we could simply visit each house. But from the scale of the sun, the planets are like motes of dust themselves, drifting through a vast electromagnetic storm. The space between them isn't a highway, it's the solar system itself. The planets are just the punctuation marks in a sentence written mostly in empty space. It's curious to think how different that emptiness feels depending on where you stand. From Earth, looking up at the night sky, space seems distant, unreachable. But from space, looking back, you see how fragile and small the world can be. You realize that the blackness between planets isn't something to fear. It's the foundation that holds everything together. Without that open space, there would be nowhere for planets to move, no room for gravity to create orbits, no stage for light to travel across. The emptiness is what gives the solar system its shape. When spacecraft leave Earth and begin their long journeys, they spend most of their lives in this in-between. They coast silently for years through the dark, occasionally adjusting their path, sometimes passing near a planet to steal a bit of momentum through gravity's pull. Missions like Voyager, Cassini, and New Horizons are testaments to how much of exploration is about patience. They remind us that discovery often happens not at the destination, but in the journey itself, the long, quiet crossing between worlds. And so, when we talk about what lies between planets, it's not nothing. It's plasma and dust, light and radiation, magnetism and gravity. It's history too, the remnants of creation still floating through space. The solar system isn't a collection of separate objects. It's a single, connected system of energy and matter, all of it moving together through the galaxy. Between planets lies the memory of how everything began. If you could trace every particle, every ray of light, you'd find that it forms a web. The sun sits at the center, but every planet, every moon, every fragment of rock contributes to the structure. When a comet passes through, it leaves trails that persist long after it's gone. When a meteor burns in Earth's sky, it's a piece of that shared material returning home. Even the faintest dust between worlds carries the signature of what once was. Ancient collisions, supernovae, the birth of stars long before our own sun. In that sense, the quiet between worlds isn't just distance, it's continuity. It's the background that connects everything. And as we move deeper into our understanding of the solar system, we begin to see that what appears empty is often full of meaning. The particles, the radiation, the subtle magnetic flows, all of it forms an invisible architecture, the scaffolding of our cosmic home. If you let your thoughts drift there, imagine floating between planets, far from any surface or sound. You wouldn't feel the passage of time the same way. Days and nights would lose their meaning. The sun would rise nowhere and set nowhere. The only constant would be motion, the slow, unending movement through the quiet. You might start to sense that this is what balance feels like. Not stillness, but a continuous, gentle flow. When we think of the solar system, we often picture it floating in a great emptiness, an island of warmth in a cold cosmic sea. But that picture isn't quite right. The solar system doesn't hang in a perfect vacuum. It swims within a much larger environment, part of a vast ocean of gas, dust, radiation and magnetic fields that stretch between the stars. To understand what lies between the planets, it helps to look outward a little farther, to see where those boundaries begin and where the influence of our own star starts to fade into something even larger. The space between the stars is called the interstellar medium. It's the background through which the sun travels as it orbits the centre of the Milky Way. Every second, the solar system moves roughly 20 kilometres through this invisible sea, trailing its magnetic bubble like a wake behind a ship. The edge of that bubble marks the true frontier between what belongs to the sun and what belongs to the galaxy. And while that boundary might sound like the end of our solar system, it's not a wall or a shell. It's more like a gradient, a region where the influence of one environment slowly gives way to another. When the solar wind races outward from the sun, it expands freely at first. It carries with it the sun's magnetic field and a steady stream of energetic particles. But the farther it goes, the weaker it becomes. Eventually, the outward pressure of the solar wind balances the inward pressure of the thin gas that fills interstellar space. That balance point is called the heliopause, and it lies more than 100 times farther from the sun than Earth does. Out there, the solar wind slows, and the particles from other stars begin to mingle with our own. Voyager 1, launched in 1977, was the first spacecraft to cross that boundary. It took nearly 40 years to reach it. When it did, the instruments on board recorded a sudden rise in the number of cosmic rays, high-energy particles arriving from beyond the solar system. At the same time, the density of charged particles changed, signalling that the probe had entered a new environment. That moment marked humanity's first physical step into interstellar space. It was an extraordinary confirmation of what scientists had long suspected, that the sun's domain has an edge, and beyond it lies a much older, wider world. What fills that wider world is astonishingly sparse, but not empty. The interstellar medium contains hydrogen, helium, traces of heavier elements, and dust grains forged in the explosions of ancient stars. Those grains drift for millions of years before becoming part of new stars, planets, and comets. In a sense, the material that makes up our solar system once belonged to others. The atoms in your body were shaped in the hearts of long-dead suns, scattered through space, and gathered again when our own star was born. Between stars lies the memory of all that creation. The density of that medium is almost impossible to grasp. In the quiet regions between stars, there may be just one atom per cubic centimetre. In the thickest clouds, where new stars form, there can be thousands. Even at its densest, it would still qualify as a vacuum by earthly standards. yet it's enough to carry light, to shape magnetic fields, and to influence the motion of entire systems. Over millions of years, as the sun moves through the galaxy, it encounters different regions of that interstellar gas. Sometimes denser, sometimes thinner, these regions can compress or stretch the heliosphere, changing how far the solar wind reaches. The space between the stars is not uniform, it's patchy, structured, and alive with motion. There are regions of hot plasma, cooled remnants of supernovae, and vast clouds of cold gas where gravity is beginning to gather material into new stars. These clouds, known as molecular clouds, are the nurseries of the galaxy. Inside them, pressure and temperature rise until hydrogen begins to fuse and a new sun ignites. Around each of those suns, disks of dust and gas swirl, slowly coalescing into planets and moons. What we see between our planets today, the dust, the wind, the faint magnetic fields, is a smaller reflection of that larger process. The solar system carries with it the echo of its birth environment. If we could look at the Milky Way in radiolight, we'd see that the space between stars isn't black at all. It's a web of filaments and bubbles, regions of higher and lower density shaped by the death and birth of stars. Supernova explosions blast hot cavities into the gas. Stellar winds carve tunnels and arcs. Cold clouds drift between them, dense enough to block visible light but transparent in infrared. These structures span tens or hundreds of light years. They move slowly, but over millions of years they change the shape of entire galactic arms. The sun happens to reside in a particularly quiet neighbourhood called the local bubble. It's a region about 300 light years across, filled with hot, thin gas left over from ancient supernovae. The sun and its planets drift through this cavity, surrounded by slightly denser clouds at the edges. That environment affects how the heliosphere behaves. Because the surrounding gas is so thin, the solar wind can expand farther before it's stopped. If the sun were moving through a denser region, the boundary of the heliosphere might be much closer, exposing the outer planets to more cosmic radiation. In that sense, even the space between stars influences life on Earth. It's easy to think of the interstellar medium as static, but it's constantly in motion. Shock waves from supernovae ripple through it, compressing and heating the gas. Magnetic fields twist and reconnect, channeling charged particles across light years. Cosmic rays, the high-energy nuclei of atoms, stream through the galaxy, bouncing off magnetic irregularities and spreading energy everywhere. Every cubic centimetre of interstellar space carries traces of these events. The universe is never at rest, even in the places that look empty. Inside the solar system, the sun's wind shields us from most of those cosmic rays, but some still make it through. They strike Earth's atmosphere, creating showers of secondary particles. Over long timescales, changes in the strength of the solar wind can influence how many reach the surface, which in turn may have subtle effects on our climate. The boundary between interplanetary and interstellar space isn't just a line. It's a dynamic interface that connects our environment to the galaxy beyond. You can think of the solar system as a moving bubble, a pocket of relative calm travelling through a much rougher ocean. The sun's magnetic field stretches outward in a spiral shape, carried by the solar wind. Beyond the heliopause, the magnetic field of the galaxy takes over. The two systems press against each other, sometimes pushing, sometimes blending. The result is a thin layer where charged particles mix and magnetic fields twist together. Voyager 1's instruments detected strange oscillations there, signs of plasma waves generated by this interaction. It's a kind of boundary music, played where two cosmic systems meet. For billions of years, this boundary has protected the inner solar system. Without it, the constant rain of galactic cosmic rays might have been harsher, perhaps altering the chemistry of planets or eroding their atmospheres faster. It's one of many subtle balances that make our cosmic neighbourhood what it is, and like all boundaries in space, it shifts slowly over time. As the sun moves through the galaxy, the pressure outside changes, and the heliosphere breathes in and out, expanding and contracting like a living thing. The idea that space between stars could shape the fate of entire systems is both humbling and fascinating. It reminds us that isolation in the universe is never absolute. Every star, every planet, every dust grain exists within a larger flow. Energy and matter pass from one generation of stars to the next, from one region of space to another. Even our solar system is temporary, a small structure drifting within a much greater tapestry. The emptiness between stars is the thread that ties it all together. If we look at the larger picture, the Milky Way itself is just one galaxy among billions, each filled with its own stars and interstellar mediums, each with its own version of what lies between. Some galaxies are packed with gas, forming stars at furious rates. Others are nearly exhausted, their interstellar material thin and faint. The processes that govern them are the same: gravity pulling matter together, radiation pushing it apart, and magnetic fields weaving through the chaos. The balance of those forces determines how galaxies evolve and how long their stars continue to shine. What's remarkable is how similar the small and the vast can be. The same principles that describe the space between planets, winds, fields, dust, light, also describe the space between stars and galaxies. The universe repeats its patterns at every scale. The interplanetary medium is a miniature version of the interstellar medium, which in turn is part of an intergalactic web stretching across billions of light years. From the particles drifting between Mars and Jupiter to the hydrogen clouds between galaxies, the story is one of continuity. There's no true edge, only changes in density, temperature, and scale. If you could drift far beyond the sun, past the outer planets, through the heliopause, and into the interstellar medium, you'd notice almost nothing change around you. The same deep blackness, the same faint points of light. But the instruments would know. They'd sense the rise in cosmic radiation, the shift in magnetic direction, the subtle difference in the density of particles. The change would be invisible but undeniable. You'd have left one environment and entered another, the way a diver moves from river to sea without ever seeing a line in the water. Astronomers study this invisible space not by sight, but by inference. They watch how starlight changes as it passes through the interstellar medium, how certain wavelengths are absorbed or scattered by dust. They listen to radio emissions from hydrogen atoms and use them to map the structure of our galaxy. They measure the arrival of cosmic rays and track their sources back to distant supernovae. Every observation adds a little more detail to the picture, revealing how the seemingly empty space between stars is a living, evolving part of the cosmos. For all its vastness, this medium also carries the potential for new beginnings. Every atom in interstellar space is a building block waiting to be used again. Over millions of years, gravity gathers them into clouds, compresses them into stars, and sends them back into the galaxy when those stars die. The matter that fills the space between stars is not wasted. It's recycled endlessly, reshaped into new forms. The emptiness is a kind of womb, always waiting to create again. From a human perspective, these processes unfold far too slowly to witness. The clouds move, the stars form, the dust settles, all on timescales of millions or billions of years. But in a cosmic sense, it's a continuous flow. There's no pause, no moment when the galaxy stops breathing. Between the stars, energy and matter are always on the move. The calm we perceive is an illusion born of distance and time. When spacecraft like Voyager send data back from the edge, they're not just exploring the solar system. They're giving us our first direct contact with the galaxy beyond. Their faint radio signals, travelling for hours across billions of kilometres, remind us how thin the boundary really is. One day, perhaps far in the future, new probes will follow them, travelling faster and farther, sampling the true interstellar medium, measuring the winds and fields of the galaxy itself. For now, we listen to the distant hum, the tiny fluctuations in magnetic fields that tell us we're still connected to that larger world. If the space between planets teaches us about isolation, The space between stars teaches us about connection. The sun's light, the Earth's atmosphere, the water in our oceans all exist because of that larger network of cosmic exchange. Our world is made of interstellar material, condensed and refined. The gap between the stars is not something separate from us. It's the origin and the destination of everything we are. It's strange to think that right now, as you listen, atoms of hydrogen and helium are drifting between the stars, travelling slowly toward nothing in particular. Some will never join another star. Others might be captured one day, drawn into a new system that forms long after ours is gone. Time and distance erase individuality in space. What begins in one star ends in another, carried by the interstellar wind that never truly stops blowing. When you zoom out far enough, the pattern becomes clear. Planets orbit stars. Stars orbit the galactic centre. The galaxy moves within a cluster, and the clusters drift through filaments of cosmic structure. Between all of them lies the same thing: space, thin and quiet, yet full of potential. It's not nothing. It's the fabric that connects every motion, the medium that allows light to travel, gravity to pull, and life to exist. And somewhere within that fabric our small solar system moves, a single bubble within a grander sea. Between our planets lies the space that binds them. Between the stars lies the same. Both are expressions of the same universal truth. That emptiness, when looked at closely enough, is never truly empty. As the solar system sails through this larger ocean, the boundaries blur. The interplanetary wind meets the interstellar breeze. Dust from beyond mingles with dust from within. Cosmic rays slip past the heliosphere's defences. Everything touches, exchanges, and continues. This space between the stars and the space between planets are not separate stories. They are parts of the same narrative, written on a scale too vast for our eyes but not beyond our understanding. If the solar system is floating through a sea of interstellar matter, what exactly fills the space within its own borders? What flows from the sun to shape the environment of every planet and moon we know? The space between the planets might look calm from a distance, but it is never truly still. There is a wind that blows there, one that never ceases, one that does not depend on air or weather or any of the things we know as wind on Earth. It is the solar wind, a steady stream of charged particles flowing outward from the sun in every direction. It fills the entire solar system, shaping the invisible structure of space around every planet and moon. Though we cannot see it, the solar wind is one of the most important forces that define what exists between worlds. The story of the solar wind begins on the surface of the sun, or more precisely just above it. The sun is a vast sphere of plasma, a state of matter so hot that atoms cannot hold on to their electrons. Instead, what remains is a sea of charged particles, mostly protons and electrons, moving in constant motion, stirred by the sun's intense magnetic fields. At the visible surface, called the photosphere, temperatures reach about 6,000 degrees Celsius. But above that, in the sun's atmosphere, things become far hotter. The outer layer, known as the corona, can reach more than 1,000,000 degrees. It is this extraordinary heat that gives birth to the solar wind. At such high temperatures, the particles in the corona move so quickly that the sun's gravity can no longer hold them back. They escape, accelerating outward, carrying with them magnetic fields and energy. The flow is continuous, a constant outpouring of solar material that extends billions of kilometers into space. Near Earth, the solar wind moves at an average speed of about 400 kilometers per second. During periods of heightened solar activity, it can double that speed, racing outward faster than any storm we could imagine. What makes the solar wind fascinating is how subtle it is despite its power. At Earth's distance from the sun, there are roughly 5 particles per cubic centimetre in the solar wind. That's an almost perfect vacuum by our standards. Yet because those particles are moving so fast, they can have significant effects. When they encounter magnetic fields or planetary atmospheres, they transfer energy, create currents, and shape boundaries that can stretch thousands of kilometers wide. The emptiness between planets, it turns out, is charged with motion. The solar wind doesn't blow evenly. The sun's surface is not uniform and its magnetic field is constantly changing. Regions called coronal holes, where the magnetic field opens outward, allow faster streams of particles to escape. These high-speed streams can interact with slower ones, creating waves and shocks that ripple through space. Sometimes the sun releases powerful bursts of plasma known as coronal mass ejections. These eruptions hurl billions of tons of material into space, creating temporary gusts in the solar wind that can travel all the way to the outer planets. When these disturbances reach Earth, they interact with our planet's magnetic field, producing geomagnetic storms. These storms can disrupt satellites, interfere with power grids, and create the auroras, the shimmering curtains of light that appear near the poles. The auroras are not just visual beauty, they are direct evidence of the solar wind meeting our planet's magnetic shield. Charged particles spiral along magnetic field lines and collide with atoms in the upper atmosphere, releasing energy as light. Each colour of the aurora corresponds to a different gas. Oxygen glowing green or red, nitrogen giving off purple and blue hues. The solar wind also shapes the boundaries of every other planet that has a magnetic field. Around Jupiter, for instance, the solar wind presses against the planet's immense magnetosphere, which is so large it could contain the Sun itself. When the wind strengthens, that magnetosphere compresses, and when it weakens, it expands. The same happens around Saturn, Uranus and Neptune. Even planets without strong magnetic fields like Mars and Venus feel its presence. There, the solar wind interacts directly with the upper atmosphere, stripping away particles and gradually eroding them into space. Over billions of years, this process can transform a world. Mars provides one of the clearest examples. Long ago, it had a magnetic field generated by movement in its molten core. When that field faded, the solar wind gained direct access to the Martian atmosphere. The result was a slow but persistent loss of air, with lighter gases like hydrogen and helium escaping most easily. Today, Mars still has traces of that atmosphere, but it's thin, less than 1% of Earth's surface pressure. Spacecraft orbiting Mars can detect streams of particles still being blown away by the solar wind, a faint reminder of a time when the planet was more protected. Venus experiences a similar interaction, though in a different way. Without a global magnetic field, it relies on its thick atmosphere to resist the solar wind. The upper layers of that atmosphere become ionized, forming what scientists call an induced magnetosphere. It's a temporary shield shaped directly by the solar wind's flow. The result is a kind of invisible dance between the planet and the particles streaming past it, a balance between erosion and resistance that has likely lasted for billions of years. The solar wind doesn't just influence individual planets, it defines the overall shape of the solar system's magnetic field. Because the sun rotates, the magnetic field carried by the solar wind twists into a spiral known as the Parker spiral, named after the scientist Eugene Parker, who first proposed the existence of the solar wind in the 1950s. The spiral pattern means that the magnetic field lines curve outward rather than pointing straight away from the sun. This shape affects how charged particles move through space, how cosmic rays enter the solar system, and even how dust grains drift between planets. When spacecraft travel beyond Earth, they must pass through this environment. Every probe, from Voyager to New Horizons, carries instruments designed to measure the density, speed and direction of the solar wind. These measurements help scientists understand not only how the solar wind behaves near Earth, but how it evolves with distance. Closer to the sun, the wind is faster and more turbulent. Farther out, it becomes smoother but weaker, its energy spread thin across vast distances. Even at the orbit of Pluto, more than 5 billion kilometers away, the solar wind still flows, they're reduced to a whisper of its original strength. Studying the solar wind up close has been a long-standing goal. In 2018, NASA launched the Parker Solar Probe, the first spacecraft designed to travel directly into the Sun's corona. It's a small, heat-shielded craft that dives closer to the Sun than any before it, enduring temperatures that would melt most metals. Each pass brings it nearer to the source of the solar wind, allowing scientists to measure how and where the particles gain their speed. Early results show that the solar wind is more complex than expected. Instead of a steady outflow, it flickers with tiny jets, bursts and magnetic kinks, signs of a dynamic and ever-changing system. What makes this wind so extraordinary is its dual nature. It is both gentle and violent, constant yet chaotic. It carries the Sun's magnetic field outward, shaping the space around every planet, yet it also carries the potential for disruption. Solar flares and coronal mass ejections, when aimed toward Earth, can trigger geomagnetic storms strong enough to affect communication systems, satellites, and even the flow of electricity and power lines. These events remind us that our technology, and even our daily lives, remain connected to the invisible weather of space. Despite that, the solar wind also plays a protective role. By filling the solar system with charged particles and magnetic fields, it creates a kind of shield against some of the more dangerous cosmic radiation that arrives from outside the galaxy. The heliosphere, the vast bubble formed by the solar wind, acts as a barrier, deflecting a significant portion of those high-energy particles. Without it, the radiation environment around Earth would be much harsher. It's an ironic balance. The same wind that can disrupt satellites also shelters us from a more hostile universe. The breath of the solar wind also carries information. Every fluctuation in its speed or density tells scientists something about the processes happening on the Sun. Spacecraft that monitor the solar wind act like weather stations, detecting changes that can forecast solar storms days before they reach Earth. Missions such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, keep watch, studying the Sun's surface and its eruptions. Their data are used to predict space weather, helping protect astronauts and satellites from sudden surges of radiation. But beyond its practical significance, there's something deeply fascinating about the solar wind as a natural phenomenon. It's a continuous connection between our star and every planet. The particles that make up the wind are born in the Sun's atmosphere, travel outward for days or weeks, and eventually pass by Earth, Jupiter, and beyond. In that sense, the solar wind is like a thread, tying the entire solar system together in a single flow. Every world is touched by it, every moon and asteroid bathed in its particles. Even the smallest objects, such as dust grains, feel its influence. The solar wind exerts a slight pressure, enough to push tiny particles inward or outward depending on their size and charge. Over time, this pressure, combined with sunlight, clears dust from the inner solar system, driving it either toward the Sun or out beyond the planets. The result is a kind of balance, a slow, invisible cleaning that keeps the space between planets from becoming too crowded. If you could stand somewhere between Earth and Mars and somehow see the solar wind, it would not look like a breeze or a cloud. It would be invisible to the eye. But if you had instruments to sense charged particles, you would feel a constant stream, unending and uniform. Occasionally a burst would pass, a shock wave from a distant solar eruption. The magnetic field would twist and shift, then settle again. The silence would never break, yet everything around you would be in motion. The solar wind also influences comets, those icy wanderers that pass through the solar system from distant regions. When a comet approaches the Sun, its ices begin to vaporize, releasing gas and dust. The solar wind interacts with that material, sweeping charged particles away to form the comet's ion tail, which always points directly away from the Sun, regardless of the comet's direction of travel. Watching a comet in the night sky is, in a way, watching the solar wind at work. its invisible breath shaping the visible beauty we see from Earth. Over time, the solar wind even alters the space around the sun itself. The constant outflow of particles carries away angular momentum, gradually slowing the sun's rotation. It's a minuscule effect, spread over billions of years, but it's one of the ways stars evolve. Younger stars tend to have stronger winds and faster rotation. As they age, their winds carry away energy, and their spin slows. By studying the solar wind, astronomers learn not only about our own sun, but about stars throughout the galaxy. There's a quiet grandeur in knowing that this wind connects us to something so immense. Every breath of air on Earth ultimately comes from the sun's energy. Every flicker of auroral light, every magnetic ripple, every subtle effect on space and weather traces back to that continuous flow of plasma. The solar wind is not a storm to fear, but a reminder that we live within the extended atmosphere of a star. Our world, like all others in the solar system, drifts in that glowing exhalation. The more we study it, the more we realize how much of our solar system's character is defined by that breath. It determines how radiation moves, how dust travels, how planets lose or keep their atmospheres. It shapes the very boundaries of our cosmic home. The solar wind is both the sculptor and the heartbeat of the space between planets. As you imagine that invisible flow, reaching outward past Mercury, past the orbit of Earth, past Jupiter's moons and Saturn's rings, remember that it never truly stops. It stretches all the way to the heliopause, where it finally meets the faint breath of the galaxy beyond. There, the sun's influence ends, and the interstellar medium begins. But even at that edge, the two mingle slightly, sharing particles and fields. The solar wind does not vanish, it simply becomes part of something larger. Drifting quietly through the same space as the solar wind, there's something far smaller, slower, and older. Tiny grains of matter, no larger than specks of smoke, move through the solar system in great invisible streams. They're the dust of space, scattered between the planets, remnants of collisions, comets, and the birth of the worlds themselves. You could call it cosmic pollen, a fine, ancient residue carried by the solar wind, glowing faintly when it catches the light, and silently recording the history of everything that has ever passed through the solar system. If you were to scoop up a handful of the space between Earth and Mars, you'd find it nearly empty, but not perfectly so. In every cubic kilometre of that void, there are countless dust grains, some just a few molecules wide, others large enough to glimmer as they tumble. These are fragments of rock, glass, carbon, and ice, drifting on orbits that have lasted for thousands or even millions of years. Together they form what's known as the interplanetary dust cloud, a vast and delicate structure that fills the solar system like a thin haze. It's not dense enough to obscure the stars or slow a spacecraft, but it's dense enough to scatter sunlight, creating a faint glow that humans have seen for centuries without quite understanding it. That glow is called zodiacal light. On a clear night, away from cities and bright skies, you might see it near the horizon just after sunset or before dawn, a soft triangular glow rising from the line of the ecliptic where the planets travel. It's sunlight reflecting off the interplanetary dust, the same way light reflects off the air to create the colour of the sky during the day. Only here, there's no atmosphere, just countless grains of ancient debris suspended across hundreds of millions of kilometres. Seeing zodiacal light is like catching the sun's breath made visible by dust, the gentle shimmer of a solar system still alive with the movement. The origins of this dust are varied and complex. Some of it was born in violence, microscopic shards from asteroid collisions that shattered larger bodies into smaller ones. Some comes from comets, which shed material every time they approach the sun. As a comet's icy surface heats and vaporizes, it releases gas and dust into space, leaving behind a trail that can stretch millions of kilometers. Over time, these trails spread out, forming rings and bands of dust that linger long after the comet itself has moved on. And some dust is even older, predating the solar system itself, carried here from interstellar space, grains that condensed around distant stars billions of years ago, survived supernova explosions, and drifted through the galaxy until they found a home in the sun's gravitational reach. Each grain is a record. Embedded in it are atoms and isotopes that tell stories of extreme heat, freezing cold, radiation, and cosmic collisions. Scientists collect some of this dust using spacecraft like NASA's Stardust mission, which in 2006 returned tiny samples from a comet's tail. Inside those microscopic fragments, researchers found complex organic molecules, carbon compounds that can form the building blocks of life. It's a humbling thought that even the smallest particle drifting between planets may carry traces of chemistry that connects stars to life itself. The solar system is constantly recycling this dust. New material is created by collisions and cometary shedding, while old grains are destroyed by sunlight and friction. Sunlight itself plays a subtle but powerful role in shaping the dust's journey. Photons, particles of light, carry momentum, and when they strike a dust grain, they exert a minuscule push. This pressure, called radiation pressure, can slowly nudge particles onto new paths. Very small grains may even be blown completely out of the solar system, pushed along by the continuous flow of light. Slightly larger ones spiral inward over thousands of years, pulled by the sun's gravity while losing energy to a faint drag effect known as Poynting-Robertson drag. That drag happens because, from the dust grain's point of view, sunlight doesn't arrive perfectly head-on. As the grain orbits the sun, the light seems to come from a slightly forward angle, and this subtle shift causes it to lose orbital energy and gradually move closer to the sun. Eventually, such particles either fall into the sun or collide with other bodies, perhaps joining the surface of an asteroid or settling on a planet. Every grain's path is shaped by this quiet contest between gravity pulling it inward and light pushing it away. The result is a slow, endless circulation of matter, a cosmic version of dust carried on air currents that never truly stop. Closer to the planets, the distribution of dust becomes more structured. The gravitational pull of Earth, Venus, and Mars gathers dust into faint bands along their orbits. Earth's orbit, for example, is surrounded by a subtle cloud of particles that forms a kind of ring, though one so thin it can only be detected with sensitive instruments. These bands of dust are like the faintest footprints, marking the paths of the planets as they travel through space. Some scientists even suggest that, under the right conditions, these rings can influence the movement of more dust, collecting material in resonant patterns the same way ripples on water can trap floating leaves. There's also a population of dust that originates from the asteroid belt between Mars and Jupiter. When asteroids collide, they release debris that can be ground down over time by further impacts and radiation. Much of this material migrates inward, joining the general interplanetary dust cloud. Occasionally, larger fragments enter Earth's atmosphere as meteors, burning brightly in a brief flash of light. Most are no bigger than grains of sand, but every day Earth collects about 100 tons of this material, microscopic particles that fall unnoticed onto oceans, deserts, and ice caps. Over billions of years, an entire layer of cosmic dust has accumulated on Earth, invisible but ever-present, connecting us physically to the rest of the solar system. If you were to float somewhere between Earth and Jupiter and look around, you wouldn't see this dust with your eyes. It's too faint, too sparse, but if you could enhance your vision 1,000-fold, you might notice a soft haze illuminated by sunlight, the faintest suggestion of movement. You'd see delicate bands of brightness where dust is denser, especially near the plane where most planets orbit. You might notice a faint glow trailing behind Earth, a wake of particles caught in its gravitational field. It wouldn't look like fog or smoke. It would be clearer, more like light seen through water, a shimmer of suspended motes carried by invisible tides. Instruments aboard spacecraft can detect this dust not by sight but by impact. Tiny grains strike detectors at high speed, releasing brief pulses of electric charge that reveal their presence. Each impact tells scientists something about the grain's size, velocity, and direction. The Cassini spacecraft, which orbited Saturn for more than a decade, carried a dust analyzer that detected particles originating not only from Saturn's rings, but also from beyond them, even some thought to come from interstellar space. These detections showed that the solar system is not isolated. Particles from the galaxy beyond constantly flow through it, merging with local dust and continuing their slow journey. The behavior of dust near the outer planets is particularly interesting. There, far from the sun, light pressure is weaker and the solar wind is thinner. In that environment, dust can linger much longer. Moons and rings around planets like Saturn act as sources of new material, releasing fine particles when micrometeoroids strike their surfaces. Those particles can form temporary halos and arcs around the planets, illuminated faintly by sunlight. Saturn's E-ring, for instance, is maintained by material ejected from the Moon Enceladus, where geysers of water vapour and ice spray continuously from its south pole. Each grain of ice joins the ring, reflecting light as it drifts, a reminder that even far from the sun, the process of dust creation never stops. On smaller scales, dust interacts with magnetic fields and plasma, gaining or losing electric charge as it moves through the solar wind. These interactions create complex dynamics that scientists are still unravelling. A dust grain isn't just a passive particle, it responds to the electromagnetic environment around it. Depending on its charge and the surrounding magnetic field, it can be trapped, accelerated, or redirected. In that sense, the dust cloud between planets behaves almost like a living medium, constantly shifting and rearranging under the combined influence of gravity, light, and magnetism. When we look at the solar system as a whole, we tend to think of the planets and moons as the main components, but the total number of dust grains dwarfs them in count. The total mass of all this dust might only equal a small asteroid, yet in terms of quantity, there are more particles of dust in the solar system than there are stars in the Milky Way. Most are too small to ever be noticed, but together they form the connective tissue of the solar system, linking planets, comets, and asteroids in a single shared environment. These grains also carry clues about the earliest days of the solar system. Some meteorites contain tiny inclusions called pre-solar grains, microscopic crystals that formed around other stars before the sun existed. They survived the collapse of the cloud that created our system and became embedded in the materials that would one day form planets. Studying them allows scientists to trace the solar system's ancestry, to understand what kinds of stars contributed material to its formation. Each grain is a survivor from a time before time as we know it, a fragment of a story billions of years old. The dust between planets also acts as a laboratory for chemistry. On their surfaces, exposed to ultraviolet light and cosmic radiation, simple molecules can form more complex ones. Some scientists believe that this interplanetary chemistry could have seeded early Earth with organic compounds long before life began. Microscopic particles entering Earth's atmosphere can deliver these molecules intact, protected within their mineral shells despite the brief flash of heat during entry. In this way, cosmic dust becomes not just a remnant of creation, but a messenger of potential life. For most of history, this dust went unnoticed. Ancient astronomers saw zodiacal light but did not understand its source. It wasn't until the mid-20th century that scientists began to realize how pervasive it was. Radar systems used to detect meteors started picking up faint signals from much smaller particles. Spacecraft began to measure impacts. Gradually, a picture emerged of a solar system filled with fine matter, invisible yet influential. Today, we can even map the dust distribution using infrared observations from space telescopes. These maps reveal complex structures, bands, arcs, and trails that tell the ongoing story of collisions and migrations. From a certain perspective, the solar system is a constant conversation between the large and the small. Planets and asteroids move on predictable paths, while dust swirls and disperses around them, responding to every subtle change. The balance between these scales keeps the system alive. The dust records the movement of everything that happens, carrying traces of past events forward through time. It's a record keeper, a silent archivist of cosmic history. Imagine for a moment being able to see that history written in the light. Each tiny glint from a grain of dust is a fragment of memory. A piece of a comet, a shard of an asteroid, a molecule born in the atmosphere of a dying star. Together, they form a slow, constant snowfall of cosmic material drifting between worlds. It's so gentle that it might take 1,000,000 years for a single grain to cross the distance from Jupiter to the Sun, yet that grain will endure, changing shape and charge, joining and leaving countless flows along the way. In the inner solar system, closer to the Sun, the dust is warmer. It absorbs sunlight, reaching temperatures of a few hundred degrees. Farther out, near Neptune and beyond, the dust is colder than the darkest ice on Earth. Yet the processes remain the same. Everywhere, light pushes, gravity pulls, and collisions reshape. Dust doesn't just fill space, it defines it. Without this fine material, the solar system would be a collection of lonely spheres, moving through a sterile void. With it, there's connection, texture, and continuity. From Earth's orbit to the edge of the heliosphere, the dust population gradually thins but never disappears entirely. Even beyond the influence of the Sun, interstellar dust drifts in, crossing the boundary and joining the local environment. The Parker Solar Probe and other missions continue to study these interactions, tracing how dust grains survive or vaporize as they encounter the intense heat near the Sun. Some evaporate completely, contributing their atoms to the solar wind, completing a cycle that began billions of years ago. And so, between the planets, this invisible snow continues to fall, each grain a traveller, each one a tiny fragment of something larger. Together they create the faint light that glows in the night sky, the subtle haze that connects the planets we can see to the vast space we cannot. The dust tells us that even emptiness has a memory. It shows that the solar system, for all its distance and silence, is not an empty stage but a living environment, still shaped by the smallest of things. As the sunlight continues to pour outward, the dust catches it, scattering it in every direction, reminding us that even in the darkest reaches between planets, light always finds something to touch. If you could drift between the planets long enough, you might begin to sense that something invisible is always present, something that moves without motion and touches everything without weight. It's not wind, not dust, not light, but something deeper and quieter. A structure that underlies all of them. This is the whisper of magnetic fields, the unseen framework that threads through the solar system, shaping the movement of particles and defining the space between worlds. Magnetic fields are everywhere in the universe, though we rarely notice them. On Earth, they quietly guide compasses and protect us from radiation. Around the Sun, they control the flow of the solar wind and give rise to the strange, shifting architecture of the heliosphere. In the vastness between planets, they weave invisible boundaries, curves and spirals that determine where charged particles can go. Without them, the space between worlds would be a very different place, more chaotic, more dangerous, less alive with structure. The Sun is the source of the solar system's largest magnetic field. It's not static, but dynamic and complex, generated by the movement of plasma within the Sun's interior. Deep beneath the surface, hot gas rises and cooler gas sinks, creating immense convection currents. Because plasma is electrically charged, its motion generates magnetic fields. These fields twist, stretch, and fold as the Sun rotates, emerging through the surface in arcs and loops that we see as sunspots. Over time, the entire magnetic structure becomes tangled and stressed until it eventually snaps and rearranges itself. This process, called magnetic reconnection, releases enormous amounts of energy, producing solar flares and eruptions that travel outward through the solar wind. Every one of those eruptions carries magnetic fields into space, threading through the solar wind like strands in a river. As the solar wind expands outward, it drags the sun's magnetic field along with it. But because the sun rotates once every 27 days, those field lines don't point straight outward, they spiral. The result is what scientists call the Parker spiral, a graceful, swirling pattern that fills the solar system. It's as if the sun was spinning threads of magnetism that extend past every planet, curling outward in vast invisible waves. Closer to the sun, those magnetic lines are dense and tightly wound. As they move farther out, they stretch and thin, but they never vanish. Even near Pluto, billions of kilometers away, the faint remnants of the sun's magnetic field still ripple through the solar wind. It's hard to imagine something so immense being so delicate at the same time. If you could somehow see the magnetic field, it would look like an intricate lace of lines flowing through the void, folding and bending around planets, wrapping each one in its own variation of the same universal design. Every planet interacts with that field differently. Earth, for instance, has a strong magnetic field of its own, generated by the movement of molten iron in its outer core. This field creates a protective bubble called the magnetosphere, which stands like a shield against the solar wind. When the charged particles of the wind encounter Earth's magnetosphere, most are deflected around it, sliding along its surface before flowing past into the night side. Some, however, find their way in near the poles, spiraling down magnetic field lines and striking the upper atmosphere, creating the auroras that dance across the sky. That interaction is constant, though invisible to us. The magnetosphere compresses on the day side of Earth, where the solar wind presses against it and stretches far behind into a long tail that extends millions of kilometers into space. The shape changes with the flow of the solar wind, sometimes calm, sometimes disturbed by gusts from solar eruptions. Each variation sends waves of energy rippling through the magnetic field, producing currents and flickers of motion that instruments can detect but no eye can see. In this sense, the magnetosphere is alive, breathing in rhythm with the sun's activity. Other planets experience their own magnetic conversations with the solar wind. Jupiter, for example, has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. It's so large that if it were visible, it would appear in our night sky as wide as the full moon, despite Jupiter being hundreds of millions of kilometers away. The field traps charged particles and creates intense radiation belts that surround the planet. These belts are so energetic that any spacecraft passing through them must be heavily shielded. The field also interacts with Jupiter's moons, generating electric currents that cause auroras at the planet's poles even more powerful than Earth's. Saturn's magnetic field, though weaker than Jupiter's, is also remarkable. It's almost perfectly aligned with the planet's rotation axis, which is unusual among planets. This symmetry gives Saturn's magnetic environment a kind of quiet stability. Yet even there, the solar wind plays its part, pressing and shaping the magnetosphere, causing it to expand and contract in subtle rhythms. The result is a system that seems serene but is constantly in motion, adjusting to the balance of forces between the Sun and the planet. Uranus and Neptune add further intrigue. Their magnetic fields are tilted at extreme angles and offset from their centres, creating strange, lopsided magnetospheres that wobble as the planets rotate. This produces magnetic environments unlike any other, where field lines twist and reconnect in complex patterns. Spacecraft data show that these fields can behave unpredictably, opening and closing in ways that challenge existing models. Between the outer planets, where sunlight is faint and the solar wind weaker, these magnetic fields dominate the local environment. guiding charged particles and shaping the space around moons and rings. Even worlds without strong magnetic fields feel the influence of magnetism. Mars, though it lost its global magnetic field long ago, still has patches of magnetized crust left over from its earlier history. These local magnetic fields create small scattered bubbles in the atmosphere where the solar wind cannot penetrate easily. Venus, as mentioned before, develops an induced magnetic field as the solar wind flows past, forming a kind of temporary magnetosphere carved directly by the sun's energy. Each interaction, unique in shape and scale, is a conversation written in magnetism. The whisper of magnetic fields is not a sound in the ordinary sense, but it can be heard if you know how to listen. Spacecraft equipped with instruments called magnetometers measure changes in magnetic field strength and direction as they move through space. When those measurements are converted into audio frequencies, the data can be transformed into eerie, wavering tones, low hums, sudden chirps, and sweeping oscillations. These are not literal sounds, but representations of the field's fluctuations, yet they convey something essential. Space is never silent. The magnetic fields of planets and the solar wind are constantly interacting, producing waves that travel through plasma like ripples through water. Those waves, called magneto-hydrodynamic waves, can travel vast distances. They carry energy and information through the solar wind, connecting the sun and the planets in subtle ways. When the sun releases a burst of energy, those waves race outward, altering the magnetic conditions throughout the solar system. Space weather, as scientists call it, is the sum of those interactions, the invisible storms and calm periods created by the flow of magnetism. Though we can't feel it directly, it affects everything from satellite operations to the radiation exposure of astronauts, and even, in rare cases, the stability of power systems on Earth. What's remarkable is how these enormous fields can also be delicate. A single solar flare can cause small but measurable changes in the shape of Earth's magnetosphere. During strong geomagnetic storms, the boundary between Earth's field and the solar wind, called the magnetopause, can move hundreds of kilometers inward. At the same time, energy stored in the magnetic tail can suddenly release, sending waves of charged particles rushing back toward the planet. The process is as dynamic as any weather system on Earth, though it unfolds in silence, unseen except by the instruments that monitor it. Over longer timescales, magnetic fields influence the structure of the entire solar system. They guide the motion of charged dust particles, shape the boundaries of the heliosphere, and modulate the entry of cosmic rays from interstellar space. The Sun's magnetic field even reverses polarity approximately every 11 years, flipping north and south as part of its regular activity cycle. This reversal doesn't happen all at once. Instead, the magnetic field becomes tangled and chaotic before reorganizing itself in the opposite direction. During these transitions, solar activity tends to peak, with more sunspots, flares and eruptions, all of which send new patterns of magnetism flowing outward into space. This constant reshaping of the solar magnetic field is what keeps the interplanetary environment alive. The boundaries between regions of different polarity form current sheets, vast, thin layers where electric currents flow through space. These sheets undulate with the sun's rotation, creating a structure sometimes called the heliospheric current sheet. The largest such structure in the solar system, it's often compared to a ballerina's skirt, rippling and twisting as it extends outward with the solar wind. As Earth and the other planets move through it, they experience periodic changes in magnetic orientation, a subtle rhythm that echoes the sun's heartbeat. Understanding magnetic fields also helps explain how planets and stars evolve. Magnetic forces can influence the flow of material in young solar systems, guiding how dust and gas settle into disks that eventually form planets. Around older stars, they can drive winds that shape the surrounding space. Even galaxies themselves have magnetic fields that help organize interstellar gas on enormous scales. What happens between planets is a small version of a universal process, the constant interplay between motion, charge, and field. Despite all the instruments and theories, magnetism remains one of the more mysterious aspects of space. We can describe it mathematically, measure it precisely, and predict its effects, but its presence always feels intangible. It's something that can only be known through what it moves, not through direct perception. It bends the paths of particles, creates invisible barriers, and fills the void with structure. It's a quiet force, yet without it, space would lose much of its complexity. If you could see magnetic fields, the solar system would look entirely different. Planets would be wrapped in shimmering cocoons, their shapes distorted by solar wind pressure. Long tails of magnetism would stretch behind them, blending into the background field carried by the solar wind. The sun itself would be surrounded by loops and arcs of magnetic fire, constantly shifting and reconnecting. The space between worlds, far from being empty, would appear as a dense web of lines, each one carrying energy and information. It would be a universe of motion, though to the eye it might seem perfectly still. This invisible structure also connects to something more personal. Every atom in our bodies contains electrons moving in tiny magnetic orbits. The same physical principles that shape the solar wind's magnetic spiral govern the behavior of those electrons. The patterns repeat across scales, from the microscopic to the interplanetary. It's a reminder that magnetism isn't an external phenomenon, but part of the same fabric of physics that defines matter itself. When we look at magnetic fields in space, we're seeing the universe express one of its most fundamental behaviors. Between planets, those behaviors blend into quiet equilibrium. The magnetic field of the sun, stretched by distance, interacts gently with the localized fields of each planet. Together they create gradients, transitions, and boundaries that no human will ever see directly, but that spacecraft cross routinely. Every time a probe sends back data showing a sudden change in particle density or field orientation, it's another sign that these invisible structures are real, that they define the hidden architecture of our cosmic neighborhood. Even the faintest whisper of magnetism carries weight in the balance of forces that govern space. It dictates how radiation moves, how plasma flows, and how energy travels across the solar system. It shapes the tails of comets, directs the motion of cosmic dust, and helps maintain the boundaries of planetary atmospheres. It's the skeleton beneath the wind, the silent order behind the chaos of particles. And while magnetic fields may be invisible, they never truly fade. Long after a solar storm passes, long after the particles have scattered, the fields they disturbed continue to ripple outward, echoing through space like the aftertones of a sound that never fully ends. Those ripples blend with others, forming an unending tapestry of movement, each thread tied to the next. If you were to float there and close your eyes, you wouldn't feel the magnetic fields around you. But if you could listen through the instruments that translate them into sound, you might hear something resembling the distant hum of electricity, a low, steady murmur that never stops. It would be the whisper of the sun's magnetism, flowing past you, changing shape as it encounters the pull of planets, the drag of the solar wind, and the resistance of dust. It's the voice of the invisible structure that holds the solar system together. Light is the oldest traveller in the solar system. Every second it leaves the sun in a wave that expands outward in every direction, filling the spaces between worlds with energy. To the eye, it seems instant. Sunrise happens in a moment. Shadows shift without delay, and the sunlight that warms the skin feels immediate. But even light, as fast as it is, takes time. From the sun to Earth, the journey lasts about 8 minutes and 20 seconds. To reach Neptune, it takes more than 4 hours. Between those destinations, every ray continues uninterrupted, carrying warmth, pressure, and information across the distances that separate the planets. In the vast emptiness, light travels freely. There is no air to scatter it, no moisture to dim it, only the thin resistance of the solar wind and dust. It moves in straight lines, perfectly obedient to the geometry of space, spreading out so thinly that its intensity falls with every step away from the sun. Near Mercury, sunlight is fierce, more than 6 times stronger than what we know on Earth. Out beyond Saturn, it's pale and cold, just a faint echo of what we call day. Yet even there, it never disappears. Every planet, every grain of dust, every particle of gas is touched by it. Light is not just brightness, it is a carrier of energy, composed of tiny packets called photons. Each photon is both a particle and a wave, a dual nature that defines everything it interacts with. When photons strike matter, they can heat it, scatter off it, or be absorbed entirely, transferring their energy to electrons and setting them in motion. This process drives much of what happens between planets. It charges dust grains, powers the faint electrical currents in the solar wind, and sets in motion countless chemical reactions. Without light, the solar system would still exist, but it would be frozen, inert, and invisible. The spectrum of light from the sun is broad. Most of it falls in the visible range, the familiar colours that our eyes evolved to detect. But there's more beyond that narrow band. Ultraviolet light, though invisible, carries higher energy and plays an important role in shaping planetary atmospheres. Infrared light, at longer wavelengths, carries heat and reveals how energy moves through space. Even longer wavelengths become radio waves, subtle ripples that travel vast distances and can be detected long after the visible light has faded. The sun emits all of these, together forming a complex symphony of radiation that fills the solar system. When sunlight reaches Earth, the atmosphere filters it. The air scatters shorter wavelengths, blue and violet, giving the sky its colour, while absorbing most of the ultraviolet that could otherwise harm living cells. Other planets handle light differently. Venus reflects almost all sunlight, its dense clouds acting like a mirror, while Mars, with its thin air and dusty skies, scatters light into a soft orange haze. The outer planets, shrouded in methane and ice, filter sunlight into hues of blue and turquoise. Yet beyond all those worlds, the light itself remains unchanged, pure, steady, unbroken from its source. Between the planets, light has other tasks. It exerts pressure, though incredibly weak, on everything it touches. The same photons that warm your skin can push a dust grain through space. Over time, that pressure shapes the distribution of dust in the solar system, helping to clear out certain regions and sculpt others. Scientists have used this property to design solar sails, thin, reflective sheets that use the momentum of light to travel without fuel. In the vacuum of space with no resistance, even the faintest push can build speed. A solar sail, if given enough time, can cross millions of kilometers powered only by sunlight. Light also interacts with magnetic fields and plasma, creating complex patterns of radiation that shift and fluctuate. Some of these interactions produce phenomena known as radio emissions, bursts of electromagnetic energy that can be picked up by spacecraft and ground-based antennas. Each planet with a magnetic field produces its own signature. Jupiter's radio emissions, for example, are so strong that they can be detected from Earth with simple equipment. They fluctuate with the motion of its moons, especially Io, whose volcanic activity releases charged particles that feed Jupiter's magnetic environment. The result is a kind of electromagnetic music, rising and falling with the rhythm of the planet's internal weather. Radiation in the solar system isn't limited to light. There are other forms, equally important but less forgiving. Cosmic rays, high-energy particles from outside the solar system, stream through space constantly. Some come from distant supernovae, others from energetic processes near black holes or neutron stars. These particles move at nearly the speed of light, carrying enormous energy. When they strike atoms in planetary atmospheres, they can split them apart, creating cascades of secondary particles. On Earth, we're protected from most of this by the atmosphere and magnetic field, but spacecraft and astronauts travelling beyond those shields must endure the full force of cosmic radiation. The Sun itself adds to this background with bursts of energetic particles released during flares and coronal mass ejections. These solar energetic particles, though fewer in number than photons, can travel almost as fast and carry far more energy per particle. They can penetrate spacecraft walls, disrupt electronics, and pose risks to astronauts. Understanding their behaviour is crucial for space exploration. Missions studying the Sun, like the Parker Solar Probe and Solar Orbiter, are helping scientists map how these particles are accelerated and how they move through interplanetary space. Despite these hazards, radiation is also a source of life and transformation. On Earth, sunlight drives photosynthesis, the process that powers nearly all ecosystems. It influences weather, ocean currents, and climate. On other worlds, light interacts with ice and rock, altering their chemistry. Ultraviolet radiation on Mars breaks down carbon dioxide and releases oxygen atoms, while on Titan, Saturn's largest moon, it triggers reactions in the thick atmosphere that create complex organic molecules. Across the solar system, radiation acts as both creator and destroyer, constantly reshaping the matter it touches. One of the most striking examples of light at work is the way it reveals itself through reflection. The brightness of each planet depends on how it reflects sunlight. Earth shines with the mixed tones of clouds and oceans. Venus gleams brilliantly, reflecting nearly all light that reaches it. Jupiter's swirling clouds reflect and scatter sunlight through ammonia and water crystals, creating the planet's signature bands and storms. Even the faintest moons, covered in ice or dust, catch and return a small portion of the sun's light, glowing softly against the black background. Without that reflection, we would never see them at all. There's a deep symmetry in the way light behaves in the solar system. It begins at the sun, travels outward, touches everything it can, and is eventually absorbed or reflected back into space. Some of it escapes entirely, carrying information about the sun and its planets into the wider galaxy. That information travels for billions of years until it reaches the instruments of distant observers, or perhaps never reaches anything at all. Light is both messenger and memory. Every photon that leaves the sun carries with it a record of the conditions at that moment, encoded in its energy and direction. The same principle allows us to study the sun and other stars. By analysing the spectrum of light, the exact colours present and the pattern of absorption lines, scientists can determine temperature, composition, and motion. Every element leaves a unique fingerprint in light, and those fingerprints tell the story of the matter they came from. In the light from the sun, we see hydrogen, helium, oxygen, carbon, and traces of heavier elements. In the light reflected from a planet, we can detect gases like methane, water vapour, or carbon dioxide. Light reveals what cannot be touched. Between planets, radiation also fills the gaps left by matter. The interplanetary medium, though nearly empty, glows faintly in every wavelength. X-rays emerge from interactions between high-energy particles and dust. Infrared light radiates from warm grains heated by sunlight. Radio waves ripple through plasma, revealing the boundaries of magnetic fields. This constant background of electromagnetic energy gives the solar system its subtle, living texture. Even in the darkest regions, where the sun appears as just another star, the glow persists. Radiation behaves differently depending on distance. Near the sun, energy density is high, and particles are ionized almost instantly. The solar corona is a chaotic environment of intense radiation and magnetic turbulence. Farther out, the energy weakens, but it still governs many processes. On the icy moons of the outer planets, radiation from the sun and from planetary magnetic fields alters surface chemistry, darkening ices and creating new compounds. On Europa, Jupiter's radiation belts may help produce oxidants that could support life in its subsurface ocean. Light and radiation reach even those hidden places indirectly, influencing conditions far from their source. It's easy to imagine light as something steady and unchanging, but it fluctuates constantly. The sun's brightness varies with its activity cycle. Solar flares produce sudden spikes in ultraviolet and X-ray output, followed by gradual declines. Over thousands of years, even small changes in solar output can affect planetary climates. On Earth, the faint cycles of solar radiation have left signatures in climate records, influencing ice ages and warming periods. Light in this sense is not only illumination but a regulator of time and rhythm. There's also a subtle interplay between light and gravity. According to general relativity, gravity bends the path of light, curving it slightly as it passes near massive objects. In the solar system, this effect is small but measurable. During solar eclipses, starlight passing close to the sun appears slightly displaced, confirming the curvature of space-time predicted by Einstein. Across larger scales, this same principle allows astronomers to detect distant galaxies through gravitational lensing. Even in the quiet spaces between planets, light obeys these fundamental rules, moving along the geometry that gravity defines. If you could follow a single photon from the surface of the sun, you'd trace a path through all these interactions. It would begin deep within the sun's core as energy released by nuclear fusion, absorbed and re-emitted countless times before finally escaping into space. Once free, it would travel straight and unimpeded, perhaps brushing a dust grain, striking a planet's atmosphere, or reflecting from an icy moon. It might be absorbed by an atom, setting an electron into motion, or scattered by a particle of gas. Eventually its journey would end, converted to heat, to chemical change, or to another form of radiation. But while it lasts, it carries the story of everything it encounters. Light also defines how we perceive space itself. Without it, there would be no sense of distance or scale. Every image of the solar system, every photograph of a planet, every faint glow of a comet, depends on light reflected or emitted. When we look at a picture of Saturn's rings or the crescent of Earth rising over the moon, we are seeing light that has travelled across millions of kilometres to reach us. The distance may be enormous, but the connection it creates is immediate. In that way, light erases distance even as it measures it. Radiation beyond the visible range plays an equally important role. Ultraviolet and X-ray telescopes reveal the high-energy processes near the Sun and other stars. Infrared observatories see through dust, uncovering structures hidden from visible light. Radio antennas capture the faint whisper of charged particles moving through magnetic fields. Together, these instruments show that the solar system is not dark, but filled with signals, each one a thread in the fabric of radiation that binds everything together. For all its complexity, the dance of light and radiation is ultimately about balance. The sun emits, the planets absorb, and energy circulates endlessly. Some is stored as heat, some reflected back into space, some converted into motion or chemical bonds. The entire solar system exists in equilibrium with the light that sustains it. When the balance shifts, climates change, surfaces evolve, and atmospheres transform. Light is not merely a byproduct of the sun's existence, it is the force that shapes everything else. And though we often take it for granted, the solar system would not look the way it does without light's constant influence. The tail of a comet, the colour of Mars, the glow of Saturn's rings, even the faint hue of the zodiacal light, all are shaped by the interplay of illumination and shadow. Every photon contributes to that ongoing choreography. It's a dance that never repeats exactly, yet never stops. If you could drift between worlds and simply watch, you would see this dance unfolding quietly everywhere. Sunlight scattering through dust, plasma glowing faintly along magnetic lines, charged particles releasing energy as they strike atmospheres, darkness deepening where light cannot reach. Each moment, each interaction, a step in the same slow rhythm that connects all parts of the solar system, and somewhere beyond the light itself, beyond the gentle radiation that fills the interplanetary medium, something else travels, particles so rare and energetic that they cross the entire galaxy before reaching us. They are older than the planets, older even than the sun, moving through everything in their path with relentless purpose. Their story begins not with the sun's warmth, but with the violence of distant stars, and their journey tells us that even in the quiet space between planets, the traces of faraway worlds are always passing through. Every moment, without pause, the solar system is being crossed by travellers from beyond. They do not shine like light, and they do not move in waves that our eyes can see. They come as particles, each one a fragment of matter, accelerated to nearly the speed of light, carrying the energy of a star's explosion, a supernova, or even more distant and ancient events. They are cosmic rays, the most persistent of all visitors, and though they are invisible, their presence is constant, flowing through everything from the space between planets to the atoms in our bodies. Cosmic rays are not rays in the usual sense of the word. They are particles, protons mostly, along with heavier atomic nuclei and occasional electrons that have been stripped of their electrons and hurled into space at extreme speeds. The journey that brings them to our solar system begins in places far from here, in the shock waves of supernovae, the violent deaths of massive stars, or near black holes and neutron stars where magnetic fields twist space and accelerate matter to unimaginable energies. These particles wander through the galaxy for millions of years, bouncing off magnetic fields, changing direction countless times, until eventually some of them find their way into the sun's domain. By the time they reach the solar system, cosmic rays have no single direction. They arrive from every angle, a steady rain of subatomic particles that never stops. At any given moment, about 10,000 of them pass through every square metre of Earth's atmosphere each second. Most go unnoticed, their energy dissipating quietly as they collide with air molecules high above the surface. But some reach the ground, and a few even pass through us, leaving tiny traces that vanish instantly. There's no sensation, no harm in most cases, just the faint reminder that space is never truly empty. The sun plays a role in shaping how many of these cosmic rays reach the inner solar system. Its magnetic field and the solar wind act as a kind of shield, deflecting many of the incoming particles or slowing their approach. During periods of strong solar activity, when the wind is dense and turbulent, fewer cosmic rays penetrate deep into the solar system. During quiet periods, when the wind weakens, more of them slip through. This cycle creates a rhythm in the flow of cosmic rays that corresponds to the sun's 11-year magnetic cycle. In a sense, even these distant particles are influenced by the heartbeat of our star. When cosmic rays encounter matter, they create secondary showers of particles. In Earth's atmosphere, these collisions generate cascades of electrons, muons, and other short-lived fragments that spread outward and downward. Scientists detect these showers using ground-based observatories, equipped with arrays of detectors spread across kilometers. Each impact is a tiny event, but together they reveal a constant drizzle of energy arriving from the universe. Instruments on high-altitude balloons, satellites, and spacecraft measure the same phenomenon beyond the atmosphere, where the particles are more direct and unfiltered. In space, cosmic rays are a practical concern as well as a scientific curiosity. For spacecraft and astronauts, they represent one of the most significant hazards of long-term exposure. Unlike the solar wind, which can be predicted and partially shielded against, cosmic rays are unpredictable and deeply penetrating. They can pass through metal walls, damaging electronics and slowly altering materials. In human tissue, they can ionize molecules, breaking chemical bonds and potentially affecting cells. That's one reason why missions beyond Earth's magnetic protection must plan carefully for radiation exposure. The further from the sun's influence a traveller goes, the more direct the storm of cosmic rays becomes. Despite their potential danger, cosmic rays are also messengers, carrying information about the processes that created them. Each one is a record of an acceleration event somewhere in the galaxy. By studying their composition and energy, scientists can infer where they originated. Some come from relatively nearby supernova remnants, expanding clouds of gas and magnetic fields that continue to accelerate particles long after the initial explosion. Others may come from much farther away, perhaps from powerful jets emitted by black holes at the centres of distant galaxies. A small fraction, with energies so high they defy easy explanation, may even be linked to events at the edge of the observable universe. The highest energy cosmic rays known carry more kinetic energy than a thrown baseball, packed into a single atomic nucleus moving close to light speed. These are so rare that only a few strike Earth's atmosphere each century, but when they do, they create showers of secondary particles that spread across tens of kilometers. Observatories like the Pierre Auger Observatory in Argentina and the telescope array in Utah were built to detect these extraordinary events. Each detection is a clue, a fragment of a much larger puzzle about how the universe creates such powerful particles. Between the planets, cosmic rays mix with the solar wind, creating subtle fluctuations in the interplanetary environment. The two populations of particles, solar and galactic, interact, generating waves and turbulence in the plasma that fills space. Instruments aboard spacecraft can detect these variations as changes in particle density or magnetic field strength. The result is an invisible weather system, shaped by both local and distant sources. It's not weather as we know it, but a ceaseless movement of charged particles and fields that fill the space between planets with activity. Sometimes the Sun itself produces its own version of a cosmic storm. During powerful solar flares and coronal mass ejections, particles are accelerated to near-light speeds within the solar system. These solar energetic particle events can reach Earth in less than an hour after a major eruption, flooding the space environment with radiation. They are shorter-lived than the background of galactic cosmic rays, but far more intense. For spacecraft caught in their path, these storms can be dangerous. Satellites can lose data or suffer damage, and astronauts outside the protection of Earth's magnetic field must take shelter. These are the solar system's internal storms, sudden, violent bursts within an otherwise steady flow. From a distance, these events would be invisible to the eye. There would be no flash, no sound, no motion. Yet instruments would record a surge of charged particles, a rising hum in radiation detectors, a shift in magnetic readings. In a sense, the solar system is always in motion between calm and disturbance, between the quiet background of cosmic rays and the more localized storms born from the Sun. Even in the emptiest parts of space, these fluctuations create a kind of pulse, a sign that energy is always moving. One of the most intriguing aspects of cosmic rays is how they reveal the structure of the galaxy's magnetic field. Because these particles are charged, they don't travel in straight lines. Instead, they spiral and scatter as they encounter magnetic irregularities. Their paths become tangled, and by the time they reach the solar system, their original directions have been almost completely randomized. This makes tracing them back to their sources difficult. However, the degree of scattering also provides information about the strength and orientation of magnetic fields along the way. In that sense, cosmic rays act as probes, mapping the unseen architecture of the galaxy through their behavior. The heliosphere, the bubble created by the solar wind and magnetic field, acts as the first barrier they encounter upon reaching the solar system. As cosmic rays approach, they must push through the turbulent magnetic boundary at the edge of this bubble. Voyager 1 and Voyager 2, during their passage through that region, recorded a rise in cosmic ray intensity as they crossed from the inner solar environment into interstellar space. It was the first direct measurement of that boundary, confirming that the solar system truly floats within a protected region, surrounded by the broader cosmic sea. The transition wasn't abrupt. It was a gradual blending of environments, like moving from one layer of wind into another. Inside the heliosphere, the density of cosmic rays varies with solar activity. Instruments aboard spacecraft such as ACE and SOHO record these variations over time, showing how the Sun's magnetic field modulates the incoming flux. During solar maximum, when the Sun's surface is covered in active regions, its magnetic field is more tangled and fewer galactic cosmic rays penetrate. During solar minimum, when the Sun is quieter, more of them reach the inner solar system. This modulation creates a cycle within a cycle, linking the distant sources of cosmic rays to the Sun's changing moods. The effects of cosmic rays extend even to planetary atmospheres. When high-energy particles strike molecules in the air, they can produce chemical reactions that alter composition. On Earth, cosmic rays help create small ions that influence cloud formation, though their role in climate remains a topic of study. On Mars, where the atmosphere is thin and unprotected, cosmic radiation penetrates much deeper, interacting directly with the surface and producing measurable radiation levels. The same is true for the icy moons of the outer planets, where cosmic rays slowly modify the chemistry of surface ices, creating new compounds that can be detected by spacecraft. There's a strange duality in this process. Cosmic rays are destructive in one sense, breaking apart molecules, eroding materials, and posing challenges for life. But they also drive chemical change, creating new substances that wouldn't form otherwise. In the early solar system, they may have helped synthesize organic compounds in the dust and gas from which planets formed. On icy bodies like Europa or Enceladus, the interaction between radiation and ice may generate oxidants that could one day feed microbial life in subsurface oceans. Even in their violence, cosmic rays contribute to the chemistry that supports complexity. Radiation from these invisible storms also provides a natural background signal that scientists can use to study the history of solar activity. Certain isotopes, such as carbon-14 in tree rings or beryllium-10 in ice cores, are produced when cosmic rays strike Earth's atmosphere. By measuring their concentrations in ancient samples, researchers can reconstruct how cosmic ray flux has varied over thousands of years, revealing patterns in the Sun's behaviour long before direct observations existed. Through these traces, the invisible storms become part of the planet's record, leaving a quiet signature that endures through time. The interplay between cosmic rays, solar radiation, and planetary environments makes the space between planets more dynamic than it appears. It's not an empty gap, but a continuous field of interaction, where distant forces and local processes overlap. The cosmic rays remind us that no part of the solar system is isolated. Every planet, every moon, every grain of dust is constantly touched by particles that began their journey somewhere else entirely. In a sense, the entire galaxy is in conversation with itself, speaking through these energetic messengers that cross the void. When cosmic rays collide with solid surfaces, rocks, ice, or spacecraft, they produce a faint but measurable glow in certain wavelengths. Instruments aboard missions like the Lunar Reconnaissance Orbiter detect this radiation on the Moon, revealing how the surface absorbs and re-emits energy. Similar effects occur on asteroids and comets, contributing to their gradual weathering. Over immense spans of time, these interactions subtly darken surfaces, breaking down minerals and altering reflectivity. Even in the absence of atmosphere or erosion, cosmic rays ensure that nothing in space remains unchanged forever. To imagine what this environment feels like is difficult, because it's not something the senses can detect. The radiation has no sound, no smell, no visible form, yet it is always there. Between Earth and Mars, between Jupiter and Saturn, between the Sun and the farthest edge of the heliosphere, particles from distant stars pass through constantly. If you could slow time enough to watch one, you'd see it as a streak of energy moving through a sea of magnetic fields, deflected slightly here, scattered there, but never truly stopped until it meets something solid. The rest continue onward, crossing paths with spacecraft, planets, and dust, their journeys unending. For astronauts who have ventured beyond Earth's protective shield, the presence of cosmic rays is unmistakable even if unseen. Some report flashes of light behind their closed eyes during sleep, brief silent sparks caused by high-energy particles passing through the retina. Its direct encounter with the universe's most ancient travellers, a reminder that space is not as still as it seems. Those tiny flashes, visible only in the dark, are perhaps the most intimate evidence of cosmic rays we can experience. As technology advances, humanity is slowly learning how to live with these invisible storms. Shielding materials, magnetic deflection concepts, and radiation-hardened electronics are all designed to withstand their effects. Yet even with precautions, the awareness remains that space is filled with energy that cannot be fully avoided. The same universe that creates beauty and light also fills itself with these relentless particles, forever crossing the gaps between stars. And as they move through the solar system, they mingle with everything else: the solar wind, the dust, the magnetic fields, and the light. Together they create the environment that defines interplanetary space, an environment both delicate and vast, peaceful and full of motion. It's a space that hums with quiet energy, even when it looks still. Among all the forces that shape the solar system, gravity is the one that never stops speaking. It doesn't flicker or fade. It doesn't depend on temperature or charge or distance in the same way light and wind do. It simply is, constant and patient, reaching across space with a touch so gentle and so persistent that even the smallest particle of dust feels it. Gravity is the quiet architect of everything between planets, the invisible framework that holds every motion in place. Unlike the solar wind or cosmic rays, gravity doesn't move through space. It defines space. It's not a background but a curvature, a bending of the fabric that matter itself creates. Every mass, no matter how small, warps the geometry of the universe around it, and that curvature tells everything else how to move. The Sun, being the most massive object in the solar system, creates a deep well in that geometry. Every planet, moon, and fragment of rock follows the curves of that well, orbiting not because they're being pulled in a literal sense, but because space itself is bent in such a way that motion naturally follows circular or elliptical paths. This idea, first fully described by Einstein's theory of general relativity, changed how we understand what lies between planets. Gravity isn't a force acting across emptiness. It's a property of the emptiness itself. The space between worlds isn't passive. It's sculpted, folded, and shaped by the mass of everything within it. That shape extends far beyond the visible reach of the Sun, fading gradually but never vanishing entirely. Even out where the solar wind meets the interstellar medium, the Sun's gravity still holds a faint pull, enough to keep comets bound in distant orbits stretching halfway to other stars. If you could visualize gravity, it would look like an ocean frozen in motion. The Sun sits at the center as a vast depression, a smooth slope that extends outward. Each planet makes a smaller ripple in that surface, circling within the larger curve. Asteroids, moons, and dust add their own minute distortions. Together these shapes create a single interconnected landscape, one that defines how everything moves, where it travels, and how long it takes to return. When a spacecraft leaves Earth for another planet, it's not flying through empty space. It's gliding along this landscape, falling gracefully from one curve into another, using gravity as both guide and propulsion. The reach of gravity is infinite, though its strength weakens with distance. It's a law of diminishing influence. Near the Sun, its pull dominates, overwhelming all other forces. Farther away, the tug becomes delicate but never disappears. Even at the edge of the solar system, more than 100 times farther from the Sun than Earth, the gravitational pull remains measurable. That's why the outermost comets, in the vast region known as the Oort cloud, still belong to the Sun despite being separated by distances so vast that light itself takes months to travel them. These distant comets orbit slowly, taking millions of years to complete a single path around the Sun. Most spend their entire existence in darkness, unseen and unchanged, until a chance gravitational nudge, perhaps from a passing star or the tidal pull of the Milky Way itself, sends one inward. When it falls toward the Sun, it follows the same rules that guide every planet and asteroid, tracing a long, curved arc through space. Gravity doesn't care about scale. Whether it's a massive planet or a pebble of ice, the same principle applies. Mass shapes motion, and motion reveals mass. Closer to the Sun, gravity choreographs a more intricate dance. The planets pull not only on the Sun but on each other. Earth tugs slightly on Mars, Jupiter distorts the paths of asteroids, and Saturn's influence shapes the structure of its rings. Even tiny moons moving in synchronized orbits exert mutual pulls that change their trajectories by fractions of a degree. Over time, these subtle exchanges add up. Planetary orbits shift, stretch, or tilt by small amounts. The entire solar system wobbles gently, its center of mass moving slightly as the planets travel their paths. The Sun itself is not still. It circles that common center, drawn a few 100,000 kilometers from the geometric center of its own system by Jupiter's gravitational pull. It's through this gravitational interaction that we learned most of what we know about unseen worlds. Long before spacecraft, astronomers noticed irregularities in planetary motions that couldn't be explained by known bodies. Those slight deviations led to predictions and eventually discoveries of new planets. The existence of Neptune, for example, was first inferred from the way Uranus's orbit strayed from its expected path. Gravity betrayed the presence of something unseen. It still does today. In the outer solar system, subtle disturbances in the orbits of distant objects have led scientists to speculate about the possible existence of another planet, one yet undiscovered, its pull faint but measurable through the motions it shapes. Gravity also binds moons to planets and planets to their stars, forming systems within systems. Each moon follows its parent planet while sharing the larger orbit around the Sun. The combined effect produces delicate balances known as resonances, ratios of orbital periods that repeat in regular patterns. For instance, 3 of Jupiter's largest moons, Io, Europa and Ganymede, are locked in a 1.24 resonance. Every time Ganymede completes one orbit, Europa completes 2 and Io completes 4. These alignments keep their motion stable over billions of years, but also create subtle tidal effects that warm their interiors. In Europa's case, that internal heat may sustain a subsurface ocean beneath its icy crust. Gravity, in this way, becomes not only a force of motion but also a source of energy. On Earth, we experience this gravitational connection through tides. The moon's pull lifts the ocean slightly as it passes overhead, creating rhythmic rises and falls that have continued since long before life began. The Sun adds its own influence, amplifying tides when aligned with the moon and diminishing them when out of phase. This ceaseless movement, gentle and predictable, is one of gravity's most visible effects, yet it's only a fraction of what happens elsewhere. On Jupiter's moon, Io for example, the tidal forces are so extreme that its entire surface flexes by more than 100 meters every orbit, driving volcanic eruptions across its surface. On other moons, those same forces knead ice and rock until they melt within, creating oceans in worlds that otherwise appear frozen. Every orbit, every tide, every small adjustment of motion is part of gravity's dialogue across the solar system. It's a conversation conducted in silence, yet one that defines the behavior of everything from dust to gas giants. Gravity dictates where planets can form and how they stay stable. It decides which asteroids become moons and which wander free. It determines the shapes of rings, the tilts of orbits, the slow precession of rotational axes. Even chaos in space follows gravitational logic, never random, only complex. The same laws that govern these motions apply on scales far beyond the solar system. The Milky Way itself holds together through gravity, its stars orbiting the galactic centre much as planets orbit the Sun. Galaxies group into clusters, clusters into superclusters, and the structure of the universe as a whole, the cosmic web of filaments and voids, is defined by gravity acting over unimaginable distances. In this way, the same force that makes an apple fall also shapes the fate of galaxies billions of light years away. Gravity is universal not just in its reach, but in its language. The equation that describes it is the same everywhere, unchanging and absolute. In the regions between planets, gravity's effects are subtle but ever-present. A spacecraft coasting through the inner solar system follows a curved path dictated by gravitational balance. Engineers and navigators must account for every nearby mass, every small perturbation. When they send a probe to Jupiter or Saturn, they often use what's called a gravity assist, a maneuver that harnesses a planet's motion to change the spacecraft's speed and direction. By flying close to a planet, the craft gains or loses energy relative to the Sun, effectively stealing a bit of the planet's orbital momentum. This technique allows missions to travel farther with less fuel, turning gravity from an obstacle into an ally. The Voyager missions, launched in 1977, used a rare alignment of the outer planets to perform a series of gravity assists, slingshotting from Jupiter to Saturn, then onward to Uranus and Neptune. Those encounters allowed Voyager 1 and 2 to escape the Sun's gravitational hold entirely, entering interstellar space decades later. The same principle continues to guide missions today, a demonstration of how understanding gravity can turn the very structure of space into a highway. But gravity isn't just a navigational tool, it's also a storyteller. It reveals mass where light cannot. When a planet passes in front of a star, the tiny wobble in the star's motion caused by the planet's pull allows astronomers to infer its presence. This method, called radial velocity measurement, has led to the discovery of hundreds of exoplanets. In a similar way, variations in the orbits of objects in our own solar system help scientists estimate the distribution of unseen mass, whether it's dark matter in the galaxy or smaller bodies hidden in the outer regions of the Sun's influence. Despite its constancy, gravity is not always steady in its effects. Over immense timescales, the orbits of planets shift in complex patterns. Small gravitational interactions accumulate, leading to cycles of eccentricity and tilt that can influence climate. On Earth, these cycles, known as Milankovitch cycles, have contributed to the timing of ice ages and interglacial periods. The connection between orbital motion and life is profound. Gravity doesn't just hold the planet in place, it also shapes the rhythm of its environment. In the space between planets, gravity and motion create regions of equilibrium known as Lagrange points. These are spots where the gravitational forces of two large bodies, such as the Earth and the Sun, balance in just the right way that a smaller object can remain almost stationary relative to them. Spacecraft often occupy these points because they provide stable vantage positions. The James Webb Space Telescope, for example, orbits near the second Earth-Sun Lagrange point, where it can stay in constant alignment with Earth, while keeping its instruments shaded from direct sunlight. These points are like eddies in the gravitational flow, places of calm in the midst of continuous motion. Even the smallest fragments of matter obey gravity's command. Dust and gas drawn together over time can form clumps that grow into asteroids, and sometimes, if enough mass gathers, into planets. This process, called accretion, is how the solar system began. In the earliest days, the Sun's gravity pulled surrounding material into a disk. Within that disk, smaller concentrations of matter attracted each other, growing through collisions and mergers. Gravity was the sculptor of those beginnings, turning chaos into order through simple attraction. Every rock, moon and planet that exists now is a continuation of that ancient process. In the same way, gravity shapes endings. When a comet's orbit decays, or an asteroid strays too close to a planet, the pull of gravity decides its fate. Some are flung outward, sent into new orbits, or even ejected from the solar system entirely. Others fall inward, burning in atmospheres or striking surfaces. These events, though destructive, are part of the system's evolution. Gravity recycles matter, redistributing energy, keeping the solar system in a perpetual state of motion. It's easy to think of gravity as a purely mechanical force, but it also defines the experience of time. In stronger gravitational fields, time itself passes more slowly, a consequence of the way gravity warps space-time. Near the Sun, where the curvature is deep, clocks would run slightly slower than those farther out. The difference is small, almost imperceptible, but measurable with precise instruments. Every spacecraft that communicates with Earth must account for this effect. In that sense, even time is part of gravity's long reach, stretched and compressed by the same invisible structure that shapes space. If you could drift far from the Sun into the outer reaches where its warmth fades and the stars begin to crowd the sky, you would still be within its influence. The pull would be faint, but it would never end. You would still be falling, always falling, tracing a gentle curve through the darkness. That's what gravity means. It's not a tug pulling things downward, but a path that everything follows naturally, a continuation of motion that never stops. And in that endless motion, the solar system finds its stability. Planets circle without collision, moons orbit in rhythm, and comets return again and again. Gravity keeps the pattern intact while allowing for endless variation. It's the one presence that unites all scales and timescales, the one influence that connects the immediate and the eternal. As the sun continues to shine and the planets continue to move, gravity remains the silent thread holding it all together. Even the light that leaves the sun travels along paths defined by its curvature. The dust drifting through space falls slowly toward its center, spiraling inward as if drawn by memory. And yet, despite this constancy, the universe never stops moving outward. Beyond the sun's pull, beyond the outermost comets, other forces begin to dominate. The galaxy itself has its own gravity, its own vast structure, guiding the motion of stars and systems alike. In the long reach of gravity's influence, there are travellers that do not stay in predictable orbits, worlds that move on paths both ancient and impermanent. They come from the farthest edges of the solar system, falling slowly toward the sun, spending most of their existence in darkness, only to bloom into brightness when they draw close to its warmth. These are comets, the wanderers of the deep, and their trails are among the most delicate and revealing signs of what lies between the planets. Each comet begins its life far beyond the familiar regions of the solar system. Most reside in the Oort cloud, a vast spherical shell of icy bodies that stretches tens of thousands of times farther from the sun than Earth does. Out there, sunlight is barely a whisper, and temperatures remain close to absolute zero. The comets in that distant region move so slowly that a single orbit can take millions of years. For countless ages they remain undisturbed, frozen and silent. But occasionally the gentle tug of a passing star or the faint gravitational influence of the Milky Way itself shifts their balance, setting one on a long descent toward the inner solar system. When that happens, the journey begins almost invisibly. The comet is still just an icy nucleus, a mixture of frozen gases, rock, and organic material left over from the formation of the solar system. Its size may be only a few kilometers across, yet it carries within it the same ingredients that once built the planets. As it falls inward, the sun's light grows stronger, and the cold shell begins to change. At a distance of several 100 million kilometers, the first traces of sublimation appear. Ice is turning directly into gas, forming a thin atmosphere around the nucleus. The solar wind and radiation pressure begin to act on this gas, sweeping it backward into a faint tail. What was once invisible becomes visible, the beginning of a spectacle that can stretch across millions of kilometers. There are two main kinds of tails that comets grow as they approach the Sun. The first is the ion tail, made of gas molecules ionized by ultraviolet light. These charged particles are pushed directly away from the Sun by the solar wind, forming a straight, often bluish stream that points opposite the Sun's direction, regardless of the comet's motion. The second is the dust tail, composed of tiny solid particles released as the surface warms and ices vaporize. Because dust responds to both gravity and radiation pressure, its path curves gently, creating the wide, glowing arc most visible from Earth. Together, these tails can extend for millions of kilometers, making the comet one of the largest physical structures in the solar system, even though its solid core remains small enough to fit within a single mountain range. Every comet is a balance between light and gravity. As it nears the Sun, radiation pressure tries to push its material outward, while gravity continues to pull it inward. The result is a slow shedding of mass. Some comets survive multiple passes, each time losing a little more of themselves. Others disintegrate completely, leaving behind trails of debris that spread along their orbits. Those trails, over time, become the source of meteor showers. When Earth passes through one of them, fragments burn up in our atmosphere, creating brief streaks of light that remind us of the vast cycles beyond our daily world. The most famous of these repeating comets is Halley's Comet, known since antiquity and returning roughly every 76 years. Its orbit is a long ellipse, stretching far beyond Neptune before swinging back toward the Sun. Each return follows the same principles, though not the same exact path. Gravitational interactions with planets alter its orbit slightly each time. The dust it leaves behind continues to drift, forming the material for the Eta, Aquarid and Orionid meteor showers. Halley is just one of thousands of such wanderers, each leaving behind invisible traces that connect the outer darkness to the inner light. Comets also reveal the composition of the early solar system. Their ices preserve a record of the conditions that existed more than 4.5 billion years ago. When spacecraft like ESA's Rosetta mission landed on Comet 67P Churyumov-Gerasimenko, instruments detected complex organic molecules, including amino acid precursors. These findings suggest that comets may have played a role in delivering essential building blocks of life to Earth and other planets. It's a link that turns these wandering bodies into messengers, not just of motion and light, but of chemistry and history. Beyond comets, there are other kinds of wanderers, asteroids, centaurs, and trans-Neptunian objects that travel through the spaces between planets on less stable paths. Most asteroids reside in the belt between Mars and Jupiter, where the gravitational balance keeps them in roughly circular orbits, but not all remain there. Some are nudged inward by gravitational resonances with Jupiter, their orbits elongated until they cross those of the inner planets. These are near-Earth asteroids, visitors that sometimes approach our planet closely and occasionally collide with it. Over millions of years, they too become part of the dynamic exchange between the solar system's regions, carried by the same gravitational currents that move comets. Centaurs occupy the middle ground between asteroids and comets, orbiting between Jupiter and Neptune. They are icy bodies likely originating in the Kuiper Belt, the region just beyond Neptune where many small frozen worlds reside. Centaurs are unstable, their orbits crossing those of the giant planets, and within tens of millions of years they will either be ejected from the solar system or drawn inward to become comets. They represent the transitional population, the bridge between the distant reservoirs of material and the inner solar system, where we can observe their evolution. Each one is a potential messenger from the outer darkness, carrying ancient material into the reach of sunlight. When sunlight reflects off the dust trails left by these travellers, it contributes to the faint glow of zodiacal light, the same soft cone visible before dawn and after dusk. The solar system's dust cloud is maintained in part by the constant input from comets and asteroids. Every fragment they release becomes a part of that diffuse brightness, an accumulation of billions of tiny paths overlapping in the same space. The glow we see from Earth is the visual echo of these countless journeys. Even when no comet is visible, its trace remains, suspended in the quiet, airless space between planets. The behaviour of comets also teaches us about how materials move and transform in space. As they approach the Sun, their surfaces crack and vent, releasing gas in jets that act like natural thrusters. These jets can change a comet's rotation and trajectory, creating slight but measurable deviations from their expected orbits. Over time, such changes accumulate, making each comet's return a little different. For scientists, these effects provide insight into the physical properties of cometary nuclei, their density, porosity, and composition. For the solar system, they are reminders that nothing moves in perfect repetition. Even the most ancient paths evolve with each encounter. Not all comets survive their journeys. Some are torn apart by tidal forces when they pass too close to the Sun or a planet. Others gradually disintegrate into smaller fragments that continue along similar paths. When comet Shoemaker-Levy 9 approached Jupiter in 1992, the planet's gravity tore it into more than 20 pieces. 2 years later, those fragments struck Jupiter's atmosphere, releasing energy equivalent to millions of nuclear explosions. The impacts left dark scars on the planet's clouds that persisted for months, a visible reminder of gravity's power to reshape and recycle. Even when comets vanish, their dust remains part of the solar system's fabric. The trails of older, now-gone comets continue to drift, invisible but enduring. Some of this material eventually spirals inward under the influence of sunlight and gravity, adding to the faint haze that fills the inner solar system. A few grains find their way to planetary atmospheres, burning briefly as meteors or settling gently onto surfaces. Every grain carries history, the isotopic fingerprints of ancient stars, the preserved record of a time before the Sun's birth. These wandering bodies also remind us that the solar system is not static. The region beyond Neptune, where most long-period comets originate, is influenced by passing stars, molecular clouds, and the galactic tide, the subtle gravitational pull exerted by the mass of the Milky Way. Over millions of years, these influences stir the Oort cloud, sending a few comets inward at a time. The process is slow but continuous, ensuring that the inner solar system is periodically visited by these ancient travellers. Each visit is both a renewal and a loss, a glimpse into the past and a dispersal of material that once slept undisturbed. Comets are not the only wanderers that pass through. Occasionally, objects from beyond our solar system enter and move through it, unbound by the Sun's gravity. The first such interstellar visitor discovered was Oumuamua, detected in 2017. It followed a hyperbolic path, passing through the inner solar system and exiting again into interstellar space, never to return. Its shape and origin remain mysterious. Some suggested it was a fragment of a disrupted planetesimal, others that it was more like a comet without visible activity. A few years later, a second interstellar object, Borisov, was found, a true comet, with a visible tail and a composition similar to those formed around our Sun. These discoveries confirm that the space between stars is not empty. Material from other systems drifts through ours, just as ours sends its fragments outward into the galaxy. In that sense, comets and wanderers are emissaries of connection. They blur the boundaries between solar systems, carrying dust and molecules from one environment to another. Over billions of years, countless such exchanges may occur, spreading material across the galaxy. Each system contributes to a shared interstellar inventory, a slow blending of origins that makes the universe more continuous than it appears. When a comet burns briefly in our sky, we are seeing not just a piece of our solar system, but a fragment of cosmic exchange. The chemical complexity of comets is another part of their story. Within their icy nuclei, sunlight and cosmic radiation drive reactions that produce a variety of organic compounds: formaldehyde, methanol, hydrogen cyanide, and simple sugars. These molecules, when released, interact with sunlight and create the glowing comas that surround active comets. Spectroscopy reveals their fingerprints, allowing scientists to identify them even from great distances. The diversity of these compounds suggests that the early solar system was rich in the ingredients necessary for life, and that comets acted as transporters of those ingredients to planets where conditions allowed them to accumulate. The Rosetta mission's study of Comet 67P showed that its water had a different isotopic composition from Earth's oceans, indicating that not all comets contributed equally to Earth's early water. But it also confirmed that complex organic chemistry can develop in space, far from any star. The comet's surface, dark and rough, bore signs of erosion and layering, evidence of cycles of activity and dormancy. Each perihelion passage carved new shapes, while older features faded into the dust. Over time, the comet evolved, not through life, but through interaction, with sunlight, with radiation, with gravity. From a distance, the passage of a comet is graceful. It rises from darkness, brightens as it nears the sun, and then fades again, leaving its trail behind. To watch one is to witness the solar system breathing, material drawn inward, illuminated, and released back into the void. The cycle repeats endlessly, comets appearing and disappearing on timescales that dwarf human history. Some return every few decades, others only once in millions of years. A few, disturbed by planetary encounters, are cast out entirely, destined to wander the galaxy. In that exile, they may pass near other stars, perhaps to be captured again, beginning a new journey elsewhere. When you look at the night sky and see a comet's faint tail stretched across the darkness, you are seeing sunlight scattered by dust that has travelled billions of kilometres, dust that may have formed before Earth existed. Each fragment, suspended for a brief moment in light, carries the same elements that make up air, water, and life. In that sense, the trails of comets are not only pathways through space, but through time. They connect the present solar system to its earliest origins and to the wider universe beyond. Between planets, these trails are almost invisible, yet they shape the texture of space. The interplanetary dust cloud, the faint glow of zodiacal light, the gentle showers of meteors, all trace back to the passing of wanderers. Their movement enriches the medium between worlds, turning emptiness into something dynamic, filled with the residue of motion and history. And as gravity continues to guide these wanderers on their long elliptical paths, it keeps the solar system connected to its outermost reaches. The comets that fall inward are reminders that the boundary between the sun's influence and the galaxy beyond is porous, always exchanging, always shifting. Every particle they release, every faint streak of light they leave behind becomes part of that shared environment. Every planet breathes in its own way. Some exhale thick gases into the sky, while others whisper only faint traces of vapour that drift away unnoticed. The air that surrounds a world, whether dense or tenuous, never truly ends where the surface light fades. It stretches outward, thinning gradually, dissolving into the vacuum, becoming part of the space between planets. The boundaries are not clear. They blur and merge, forming invisible bridges of atoms and ions that connect one world to another. These are the echoes of planetary atmospheres, faint extensions of each world's identity, fading into the shared environment of the solar system. An atmosphere, in the simplest sense, is a layer of gas held close to a planet by gravity. But the shape and strength of that layer depend on many things: mass, temperature, distance from the sun, and the planet's magnetic field. Close to the sun, the energy of light and heat can strip lighter gases away. Farther out, where it's colder, molecules move more slowly, and gases can remain bound for billions of years. Every planet carries its own balance, a relationship between what it can hold and what it constantly loses. The process never stops. Planets are always breathing, even if we can't hear it. Earth's atmosphere is thick enough to scatter light and create the colour of the sky. Yet even here, the air does not stop abruptly. It extends for thousands of kilometres above the surface, growing thinner with every step upward. At around 100 kilometres, the air becomes so rarefied that atoms move without colliding, yet they still circle the planet, forming the exosphere, the last trace of our world's breath. Beyond that, hydrogen and helium escape entirely, drifting into space. Those lost atoms become part of the interplanetary medium, mixing with particles from other planets and with the solar wind. A fraction of what we breathe eventually leaves the planet and joins the sun's vast domain. Venus offers a different story. Its atmosphere is immense, dense and hot, composed mostly of carbon dioxide, with clouds of sulfuric acid that trap heat and reflect sunlight. The pressure at its surface is about 90 times that of Earth's, enough to crush most spacecraft in minutes. Yet even Venus's atmosphere has an edge, where the solar wind begins to erode it. The upper layers are ionized by ultraviolet light, creating an induced magnetosphere that protects the lower air for a while. Still, over time, the solar wind carries particles away, stripping atoms from the tops of the clouds and sending them streaming into space. Every second, tons of gas escape this way. The loss is small compared to the whole, but over billions of years it becomes part of the larger balance that shapes the planet's evolution. Mars, with its thin atmosphere, shows how fragile that balance can be. Billions of years ago, evidence suggests Mars once had rivers and lakes, perhaps even shallow seas. For that to be possible, it must have had a thicker atmosphere to trap heat and maintain pressure. But when its internal magnetic field faded, the solar wind gained direct access to its upper atmosphere. Over time, it stripped away lighter molecules, carrying them into space. The process continues today. Instruments aboard orbiters like MAVEN detect streams of charged particles escaping Mars's gravity, forming a faint tail that extends behind the planet. It's an ongoing reminder that atmospheres are temporary, always in conversation with the space around them. Even small bodies can have traces of atmosphere, or what scientists call exospheres. Mercury, the smallest planet and the one closest to the Sun, has no substantial air, but it still has a thin layer of atoms released from its surface by solar radiation and micrometeoroid impacts. These particles form a fragile cloud that envelops the planet, replenished constantly as others escape. The same happens with the Moon. Though we think of it as airless, its surface gives off atoms of sodium, potassium and other elements knocked free by sunlight and impacts. These atoms drift for hours or days before escaping into space, forming a faint invisible halo that extends beyond the lunar horizon. It's not an atmosphere in the traditional sense, but it behaves as one in miniature, a transient breath that never settles. The outer planets tell a very different story. Jupiter and Saturn are made mostly of gas, with no solid surface to mark where atmosphere ends and interior begins. Their air is deep and immense, blending gradually into the planets themselves. The visible cloud tops are just the upper layers of atmospheres that extend for tens of thousands of kilometers downward, where pressure and temperature rise until gases become liquid. Yet even here, there is an upper boundary. The highest layers of these atmospheres merge into space, where the solar wind interacts with their magnetic fields. Particles from those interactions can be trapped, forming auroras near the poles just as on Earth. Jupiter's auroras are so powerful that they emit X-rays, pulsing in time with the planet's rotation. Saturn's atmosphere behaves similarly, but is shaped by its unique system of rings. The rings themselves contribute material, mostly water vapor and icy particles, that rains down onto the planet's upper atmosphere. This interaction leaves chemical fingerprints, altering the composition and temperature of the gas. The exchange blurs the boundary between ring and planet, atmosphere and space. In this environment, What escapes one world becomes part of another. Uranus and Neptune, colder and more distant, hold their gases more tightly. Their upper atmospheres are made mostly of hydrogen, helium and methane, with the methane giving Neptune its deep blue colour. The energy from sunlight is weak at that distance, yet it's enough to drive subtle chemical reactions that create haze layers. Winds on Neptune can reach more than 2,000 kilometers per hour, shaping clouds into bright streaks that circle the planet in hours. Even there, far beyond where warmth fades, motion and exchange continue. The uppermost layers of these atmospheres interact with charged particles from the solar wind, slowly releasing atoms that drift outward. Moons can also have atmospheres or exospheres, depending on their size and proximity to their planets. Titan, Saturn's largest moon, has a dense nitrogen atmosphere thicker than Earth's, with methane clouds and rain that carve rivers into its frozen surface. The air extends far above the surface, gradually thinning until it meets the magnetosphere of Saturn. There, the boundary shifts constantly, sometimes compressed by solar activity, sometimes expanding. Titan's atmosphere is also leaking into space, molecules escaping at the top and forming a faint torus along its orbit. This slow loss is balanced by chemical reactions deeper down that replenish the air, a cycle that may have lasted for billions of years. Other moons, like Europa or Enceladus, have much thinner exospheres, created by activity at their surfaces. On Europa, ultraviolet sunlight splits water molecules from the icy crust, releasing oxygen that forms a tenuous envelope around the moon. On Enceladus, geysers at the South Pole spray water vapour and ice grains into space, feeding Saturn's E-ring and creating a constant interchange between the moon and its parent planet. These processes are small compared to the thick atmospheres of planets, but they demonstrate how interconnected the solar system's environments are. Nothing exists entirely in isolation. Every atmosphere leaves its mark on the space around it. Even the giant planets influence each other's atmospheres indirectly. The solar wind and magnetic fields connect them through a shared plasma environment, where charged particles move freely from one region to another. During intense solar events, waves of energy pass through this medium, causing temporary changes in atmospheric behavior across multiple worlds. Auroras brighten, radiation belts expand, and thin layers of ionized gas rise or fall. It's a chain of responses that shows how the planets, though separated by billions of kilometers, still share the same space. One of the most fascinating aspects of atmospheres is how they fade into space. There's no hard boundary between air and vacuum. Instead, each planet's gases thin exponentially, with a few particles escaping entirely. This process, called atmospheric escape, takes several forms. Some atoms gain enough speed from thermal motion to leave the planet's gravity altogether, a process called Jeans escape. Others are stripped away by solar wind interactions, especially in unprotected regions near the poles. Still others are lost through chemical reactions that create lighter molecules capable of escaping more easily. Over time, these processes shape what a planet keeps and what it loses. On Earth, for example, hydrogen and helium escape easily, while heavier gases remain. This selective loss is why our atmosphere is dominated by nitrogen and oxygen, rather than the lightest elements. Mars, having weaker gravity and no magnetic protection, loses even heavier gases. The rate of escape depends not only on gravity, but also on temperature and solar activity. During solar storms, the upper atmospheres of planets heat up and expand, increasing the escape rate temporarily. The result is a dynamic equilibrium, always adjusting but never still. In the outer solar system, the situation reverses. There, the cold temperatures slow molecular motion, and atmospheres are more easily retained. Yet even at those distances, escape still happens. For example, Neptune's largest moon, Triton, has a thin nitrogen atmosphere that sublimates from its surface when sunlight warms it. The gas expands outward before freezing again as the moon's long seasons change. Over millions of years, this cycle erodes and redeposits the surface, a process driven by a balance between sunlight and gravity that repeats endlessly. The echoes of these processes fill the space between planets with faint traces of matter, atoms of hydrogen from Earth's upper atmosphere, oxygen from Mars, nitrogen from Titan, and countless other elements drift outward, merging with the solar wind and dust. The result is a tenuous mixture that carries signatures of every world. Instruments aboard spacecraft can detect these traces as variations in particle composition. Some regions of the solar wind are slightly enriched with elements like oxygen or carbon, evidence of the slow exchange between planets and space. It's as if each world leaves a fingerprint in the interplanetary medium, a faint but measurable echo of its presence. In some cases, these echoes return. Particles escaping from one planet can be recaptured by another. Hydrogen from Earth can travel far enough to enter the magnetospheres of other planets. Ionized oxygen from Mars has been detected farther out, caught in the solar wind and carried past the orbits of asteroids. These movements are slow and diffuse, but they link the planets in a continuous circulation of matter. Space, in this way, becomes a shared environment, filled not just with dust and wind, but with the breath of worlds. For scientists, studying these traces helps reconstruct the history of planetary atmospheres. By comparing isotopic ratios, they can infer how much material has been lost over time and what processes dominate. For instance, the ratio of heavy to light hydrogen in Venus's atmosphere shows that the planet once had far more water, much of which escaped into space as lighter hydrogen was lost and heavier deuterium remained. Similar studies of Mars reveal its past climate, indicating that most of its atmosphere was stripped away, leaving behind a frozen desert. Even Earth's history is written in these ratios, showing how the composition of air and oceans evolved together. The concept of an atmosphere extending into space also applies to the Sun. The corona, its outer atmosphere, reaches far beyond what we can see, transitioning into the solar wind that fills the solar system. In a sense, the entire heliosphere is the Sun's atmosphere stretched thin, interacting with the atmospheres of planets at every scale. The solar wind compresses magnetospheres, alters ionospheres, and sweeps away escaping gases. The planets, in turn, return atoms and molecules to that flow. What we think of as interplanetary space is in large part a meeting place of atmospheres, solar and planetary merging into one continuous system. If you could drift between worlds and somehow see these invisible layers, the view would be delicate and fluid. You'd see faint halos around the planets, not glowing with light but marked by the slow drift of particles. Around Earth, a thin shimmer of hydrogen would extend outward for tens of thousands of kilometers. Mars would have a faint wisp trailing behind it, like vapor in a vacuum. Venus would appear wrapped in a subtle haze where solar wind and gas meet. Even the Moon would carry a ghostly cloud of atoms hovering close to its surface. Together, these overlapping envelopes would give the solar system a texture invisible to human eyes but always present, a gradient of gases connecting every world to the space between them. The idea that planetary atmospheres fade into each other changes how we think of separation in space. There are no sharp borders, only transitions. Every world contributes to the larger environment, whether by releasing molecules reflecting light or shaping magnetic fields. The air you breathe on Earth once existed as atoms scattered through interstellar space, gathered by gravity and transformed through chemistry. The atoms escaping Earth today may someday drift to another system, carried by solar and galactic winds. In that sense, atmospheres are temporary expressions of matter in motion, always becoming something else. Between the planets, these faint exchanges create continuity, where we often imagine emptiness. The space between is filled not just with light, wind, and dust, but with the dispersed breath of worlds, each leaving traces of itself in the collective medium. It's a quiet dialogue, almost imperceptible, yet constant, and beyond the reach of those gases, farther still from the Sun, lies the limit of its atmospheric influence. the boundary where the solar wind gives way to the interstellar medium, marking the edge of the Sun's domain and the beginning of the space between stars. Far beyond the orbits of the outer planets, where sunlight has grown pale and faint, the solar system continues, its influence stretching into distances that seem immeasurable. The warmth that powers the inner worlds has faded to almost nothing. The glow of the sun is no brighter than a distant star, yet even here the space around is not free of its reach. A vast and invisible structure still surrounds everything that belongs to the sun. It's called the heliosphere, often described as the solar bubble, a region of space inflated by the solar wind, bounded by the slow, quiet pressure of the galaxy beyond. It's the outer edge of home, the boundary where our sun's influence meets that of the wider universe. The idea of this bubble comes from the nature of the solar wind itself. The stream of charged particles that flows from the sun never stops. It moves outward in all directions, carrying with it the sun's magnetic field and forming a continuous current of plasma that fills the solar system. Near Earth, the solar wind moves at hundreds of kilometers per second, its density still measurable and strong, but as it travels farther, it spreads thin. Eventually it slows down as it encounters the sparse but persistent gas and dust that make up the interstellar medium, the material between stars. Where those two regions meet, one driven by the sun, the other by the galaxy, the solar bubble begins to take shape. This boundary is not a hard shell, it's a set of gradual transitions, layered like the edges of an atmosphere, each defined by changes in motion, pressure, and magnetic field. Closest to the sun is the region where the solar wind still moves freely and supersonically, faster than any sound wave could travel through the same medium. At some distance, around 90 to 100 astronomical units from the sun, it slows abruptly. This is the termination shock, where the solar wind first feels the resistance of interstellar space. The particles lose speed but become hotter and denser, creating a kind of turbulent region where energy from the inner solar system begins to mingle with that from beyond. Beyond the termination shock lies the heliosheath, a vast zone of slower, compressed plasma. It's a region of transition, chaotic and dynamic, where magnetic fields twist and fold as they interact with those of the galaxy. The solar wind still flows outward here, but its strength weakens steadily. The turbulence in this region can extend for tens of billions of kilometers, filled with eddies and waves that carry traces of both solar and interstellar material. It's in this zone that the final boundary forms, the heliopause, where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Beyond it, the solar wind ceases entirely, and the sun's influence gives way to the environment between stars. The first human-made objects to cross these boundaries were the Voyager spacecraft. Voyager 1, launched in 1977, reached the termination shock in 2004, more than 7 billion miles from Earth. For nearly a decade after, it continued through the heliosheath, measuring the changing density and magnetic fields until, in 2012, it detected a sharp increase in the number of high-energy cosmic rays, evidence that it had entered interstellar space. Voyager 2 followed a similar path, crossing the heliopause in 2018. Together they provided the first direct confirmation that the solar bubble exists and that it has a definable edge. What they found was not a sharp boundary, but a gradual shift, a blending of environments rather than a wall. The data from those missions revealed that even at the edge of the heliosphere, the sun's presence is still felt. The magnetic field carried by the solar wind doesn't vanish instantly, but drapes and twists around the outer boundary, merging with the galactic field. Charged particles from the interstellar medium can enter, while some from the solar side leak outward. The boundary itself shifts and fluctuates with solar activity. During times of strong solar wind, it expands slightly, pushing outward. During quieter periods, it contracts. The entire structure breathes slowly, pulsating with the rhythm of the sun's 11-year cycle. The shape of the heliosphere is another source of fascination. For decades, it was pictured as a teardrop, rounded at the front where the solar wind faces the oncoming interstellar flow, and stretched into a long tail behind, like the wake of a ship moving through water. But newer observations suggest it may be more complex, perhaps more rounded or even shaped like a croissant, sculpted by the interactions of magnetic fields rather than by the simple flow of particles. The exact form remains uncertain because we can only observe it from within, piecing together its structure through indirect measurements. What we do know is that the heliosphere acts as a protective barrier. It shields the planets from a significant portion of cosmic radiation, deflecting high-energy particles and reducing their intensity in the inner solar system. Without it, the flux of galactic cosmic rays reaching Earth would be much greater, potentially altering atmospheric chemistry and increasing radiation levels at the surface. The solar bubble is, in a sense, a magnetic cocoon, a space where the sun's presence moderates the harsher conditions of the galaxy. It's the reason our solar system has a distinct boundary, a region where conditions remain tied to our star's activity. The interstellar medium pressing against this bubble is not empty either. It contains hydrogen atoms, dust and magnetic fields, all moving relative to the Sun at about 26 kilometers per second. The Sun, for its part, is travelling through a region of the galaxy known as the local interstellar cloud, a patch of slightly denser material a few light years across. As the solar system moves through this cloud, the shape and pressure of the heliosphere adapt to it. In a few tens of thousands of years, the Sun will move into a different region, perhaps with a different density or magnetic field, and the heliosphere will shift accordingly. The solar bubble is not fixed. It changes as the Sun drifts through the galaxy. Inside the heliosphere, the solar wind dominates, but even here, the presence of the interstellar medium is felt. Neutral atoms from interstellar space can enter, passing through the outer layers and flowing toward the inner solar system before being ionized by sunlight or collisions. Some of these atoms, particularly hydrogen, can be detected near Earth as faint signals that reveal the composition of the space beyond. In this way, the boundary between the solar and interstellar environments is not just a limit, it's a region of exchange. Material crosses in both directions, though the balance always favours the outward flow of the solar wind. The study of this boundary has become one of the most intriguing aspects of modern space science. Missions like IBEX, the Interstellar Boundary Explorer, have mapped energetic neutral atoms that result from collisions at the edge of the heliosphere. These maps show a narrow ribbon of enhanced emissions circling the sky, a feature scientists think is related to how the interstellar magnetic field interacts with the solar wind. This ribbon provides indirect evidence of the heliosphere's shape and structure, helping to fill in the picture that Voyager's direct measurements began. Newer missions like NASA's Interstellar Mapping and Acceleration Probe, IMAP, will refine that understanding, exploring how particles are accelerated and transported across these vast distances. What these studies reveal is that the solar bubble is not a quiet place. The heliosheath in particular is filled with turbulence. Magnetic fields twist, reconnect, and release energy, creating irregular waves and shocks. This activity affects how cosmic rays enter the solar system and how solar particles escape into interstellar space. It also demonstrates that even the farthest reaches of the Sun's influence are dynamic. The bubble's surface isn't smooth. It ripples and shifts under the pressure of competing forces. To imagine what this region might look like, you have to think beyond visible light. There would be no glow, no clear lines separating one environment from another. Instead, there would be gradients, densities changing slowly, magnetic fields bending gradually, particles moving from one pattern of motion into another. The transition would be silent and invisible. A spacecraft crossing it would notice only subtle changes in data. Fewer solar particles, more cosmic rays, a shift in magnetic direction. To the human senses, it would feel like nothing at all, yet it marks the point where the sun's direct power fades. The heliosphere is more than just a boundary of the solar system. It's part of how the sun interacts with the galaxy. Every star creates its own version of this bubble, a region where stellar winds balance against interstellar pressure. The galaxy is filled with these overlapping zones, each a separate domain of influence. Between them lie the true interstellar regions, where no single star dominates. Our solar bubble is just one among billions, moving slowly through the galaxy's broader magnetic field. The distances between these bubbles are immense, but their edges may occasionally touch or interact, blending materials and fields across stellar systems. This perspective changes how we think about the solar system. It's not an isolated island, but part of a vast ocean of plasma, dust, and magnetic structures. The sun's wind carves out a temporary space within that ocean, protecting its planets for a time, but always subject to the currents of the larger environment. In another few million years, the shape of the heliosphere will change again, perhaps dramatically, as the sun encounters new regions of interstellar gas. Its boundary will grow or shrink, the balance of pressures shifting as it continues its slow orbit around the centre of the galaxy. Inside this protective bubble, the space between planets feels familiar, defined by light, dust, and magnetic fields. Outside, conditions are different. The density of interstellar gas is higher, the composition richer in heavier elements, the magnetic field stronger. The temperature of the interstellar plasma is lower, but the radiation environment is harsher. When Voyager crossed into this realm, the instruments recorded these changes directly. It was the first time humanity had touched the true interstellar medium, the space between stars that has existed since long before the sun formed. What Voyager found also tells us something about the solar system's place in the galaxy. The pressure at the boundary between the solar wind and the interstellar medium suggests that the sun's environment is neither dense nor empty, but moderate. A relatively calm region compared to the more turbulent zones near supernova remnants or star-forming regions. This calm may be part of why the solar system has remained stable for billions of years. The sun travels through a gentle corridor of the galaxy, shielded by its own magnetic envelope, its planets undisturbed by major external forces. And yet, the edge of this bubble is not the end. Beyond the heliopause, the interstellar medium extends indefinitely. There are still magnetic fields, particles, and radiation, just arranged differently. The energy that flows through those spaces connects to other stars, other winds, other boundaries. In that larger structure, the sun is just one contributor, adding its particles and magnetism to the shared environment of the galaxy. The heliosphere's edge is where local influence ends, but not where connection stops. If you could travel there and look back toward the sun, you wouldn't see a visible border. The sun would appear as a bright point among countless others, its light no different from the nearby stars. But surrounding that light, unseen to the eye, would be the extent of the sun's breath, the sphere of influence that defines home. Everything familiar, from the warmth of daylight to the faint dust of zodiacal light, lies within that space. Beyond it begins a different kind of environment, colder, older, and filled with the remnants of long-dead stars. The existence of the solar bubble means that every atom within it has in some way been shaped by the sun. Even the interplanetary dust and gas that seem independent are carried by forces the sun created. The edge of the heliosphere marks the last place where those forces dominate. It's the meeting point between what the sun sends out and what the galaxy sends in. On one side, the solar wind expands. On the other, the interstellar medium presses inward. Between them lies a thin, turbulent boundary where energy, matter, and magnetism mix. The solar bubble also sets the stage for what lies beyond. Just outside it, cosmic rays flow freely, carrying energy from distant supernovae. They drift toward the heliosphere, where many are deflected, but some find their way through. This constant exchange defines the background radiation environment for all planets within. Inside, the solar wind shapes everything. Outside, the galaxy's collective forces prevail. The heliopause, then, is not just a boundary in space. It's a threshold between two scales of existence, the local and the cosmic. The more we study it, the clearer it becomes that the solar system's boundaries are not fixed lines but evolving regions of balance. The heliosphere expands and contracts, breathes and shifts, shaped by both the sun's activity and the galaxy's response. It's a dynamic equilibrium that has persisted for billions of years and will continue for billions more. When the sun eventually exhausts its nuclear fuel and becomes a red giant, the solar wind will change dramatically. The heliosphere will swell, then shrink, and finally dissipate as the sun becomes a white dwarf. The remnants of its influence will fade, leaving behind a small star surrounded by the relics of its former planets, exposed to the full flow of the interstellar medium. Beyond the heliopause, the solar wind fades into silence. The charged particles that once moved outward with the energy of the sun lose their strength, their paths bending under the influence of a different magnetic field. Here, at the threshold of interstellar space, the familiar environment of the solar system ends. Everything beyond belongs to the galaxy, a wider sea of particles and fields that stretches between the stars. It's not a place of sudden change, but of gradual transformation, a region where what was once solar becomes interstellar, where the edges blur into something older and colder. This frontier was once only imagined. For most of human history, no one knew whether the sun's influence had a boundary at all. The night sky appeared infinite, the stars like fixed points in a vast, empty backdrop. Yet now we know that the solar system is not isolated but embedded within a larger structure. The sun, like every star, carries its own sphere of influence, its own bubble of plasma and magnetism carved into the surrounding interstellar medium. Crossing that edge means entering a space that is both familiar and foreign, shaped by the same physical laws but under very different conditions. The interstellar medium, despite its name, is not empty. It's made of gas, mostly hydrogen and helium, with traces of heavier elements, along with dust grains, magnetic fields, and cosmic rays. The density is extremely low, averaging just a few atoms per cubic centimetre. But over the vastness between stars, that's enough to create structure. It's not uniform. There are regions of higher density, where gas and dust form clouds, and others that are more rarefied. The sun currently travels through a relatively warm and diffuse region known as the local interstellar cloud. Its temperature is around 7,000 degrees Celsius, but the density is low enough that the solar bubble can exist within it without being compressed too tightly. At the heliopause, the pressure from the interstellar medium and the outward flow of the solar wind are balanced. On one side, the sun's influence weakens. On the other, the galactic environment begins to dominate. The transition isn't smooth. Turbulence mixes the two, creating a region where particles from both sides interact. Voyager 1, when it crossed this boundary, detected sharp increases in galactic cosmic rays and simultaneous drops in solar particles, a clear sign that it had entered a new environment. But it also recorded that the magnetic field's direction didn't change as much as expected, suggesting that the boundary might be layered, with overlapping regions where the two environments blend gradually. The temperature beyond the heliopause rises sharply. The interstellar plasma is hotter but less dense than the solar wind it replaces. The magnetic field becomes stronger and more stable, influenced by the larger structure of the galaxy. Voyager's instruments measured a background of low-frequency plasma waves that revealed the density of the interstellar medium directly. For the first time, we could hear, in a sense, the faint hum of space beyond the sun's domain, a vibration of charged particles moving through magnetic fields that extend for light years. The interstellar frontier is not static. The sun moves through the galaxy at about 20 kilometers per second, carrying its bubble of influence along with it. As it travels, it encounters regions of different density and composition. Some areas of the galaxy contain denser clouds of gas that could compress the heliosphere, shrinking it and allowing more cosmic rays to enter. Others are more empty, letting it expand. The solar system's passage through these regions may influence the long-term environment of the planets, possibly even affecting climate and radiation levels on Earth over geological timescales. Every star in the galaxy has its own version of this frontier. Some stars produce stronger stellar winds, creating larger bubbles that overlap with their neighbours. Others, older or less active, have smaller regions of influence. In areas where stars are close together, their bubbles can merge, forming interconnected regions of plasma and magnetic field. In other places, the bubbles are isolated, separated by vast stretches of interstellar gas. The galaxy, viewed from afar, would appear like a web of invisible spheres and filaments, each one marking the reach of a star's breath. The interstellar medium itself is a complex environment, structured by both local and galactic forces. Supernova explosions send shockwaves through it, compressing gas and triggering the formation of new stars. Magnetic fields thread through the entire galaxy, guiding the motion of charged particles and influencing how matter moves. Cosmic rays, travelling near the speed of light, pass through this environment constantly, scattering off magnetic irregularities and carrying energy from distant events. The result is a dynamic, ever-changing sea of matter and energy that connects all stars in subtle ways. The boundary between the heliosphere and the interstellar medium can be thought of as the surface of contact between two winds, the outward flow of the sun's particles and the steady drift of interstellar material. Where they meet, a thin layer forms, compressed, turbulent, and filled with complex interactions. Some of the solar wind's ions are neutralized when they encounter interstellar atoms, creating energetic neutral atoms that move freely across the boundary. These particles are what missions like IBEX detect, allowing scientists to infer the structure of the heliosphere without leaving it. They reveal patterns that shift with solar activity, showing that even at the very edge, the sun's cycles still reach outward. Crossing this region means entering a realm where the sun's direct power no longer dominates. The light still shines, of course. It travels infinitely farther, but the electromagnetic and particle environment changes entirely. This solar wind, once the primary source of energy flow, is replaced by the background of the galaxy. The balance of forces becomes broader and more stable, governed not by one star but by the collective presence of many. In this way, the interstellar frontier is not an end but a transition from one kind of order to another. The Voyager's journey through this space continues. Even now, decades after their launch, they are still moving outward, more than 24 billion kilometers from the Sun. Their power sources are fading, but their instruments continue to send data, each signal taking over 22 hours to reach Earth. What they record tells us that interstellar space is not silent. It hums with plasma oscillations, magnetic fluctuations, and the faint signatures of cosmic rays. These are the background currents of the galaxy, the same ones that fill the spaces between every star, every system, every world. From this vantage, the solar system becomes just another region in a much larger structure. Its boundary, once vast beyond imagining, seems small compared to the scale of the galaxy. The Milky Way spans over 100,000 light-years, containing hundreds of billions of stars, each with its own domain. The distance that took Voyager decades to cross would be less than a step on that scale, yet that step is profound. It represents the first time an artifact of human origin has left the space dominated by our star and entered the space shared by all stars. The interstellar frontier is not only a physical threshold but a conceptual one. It marks the point where our familiar environment ends and the unknown begins. Everything we have ever experienced, every atom of air, every beam of sunlight, exists within the heliosphere. Beyond it, the rules are the same, but the context changes. The radiation is harsher, the density lower, the temperature higher, the pressure different. The magnetic field lines curve according to the shape of the galaxy rather than the sun. Time and distance stretch beyond the scales that shape the solar system. If you could drift there, you would see no visible sign of crossing. The stars would look the same. The sun would still shine as a small, bright point among others. But instruments would tell the truth. The density of particles would increase slightly, the composition would shift, and the direction of the magnetic field would no longer match that carried by the solar wind. The familiar hum of solar plasma would fade, replaced by the broader frequencies of the galactic medium. It would feel like stepping from one room into another with identical walls but different air. In this interstellar environment, the balance of energy is delicate. The pressure from magnetic fields, cosmic rays, and thermal motion all contribute to maintaining stability. The density is low enough that particles can travel for kilometers without colliding, yet high enough that collective effects, waves and currents, still occur. These interactions shape how energy moves through the galaxy, how cosmic rays are distributed, and how clouds of gas eventually collapse to form new stars. The same processes that define the solar wind on a small scale operate here on a galactic one, linking the smallest and largest structures through the same physical laws. One of the most striking realizations from studying the interstellar frontier is that it connects the story of the solar system to that of the galaxy. The sun was born from an interstellar cloud like the ones that now surround it. The material that makes up the planets, moons, and comets once floated freely in space, part of a larger structure that spanned light years. Over time, gravity pulled it together, ignited nuclear fusion, and created a star. Now, billions of years later, the remnants of that star's breath push outward again, meeting the same kind of environment from which it came. The cycle continues, the local and the galactic forever intertwined. The frontier also provides a glimpse of what happens when stars die. When a star's wind weakens or its fuel runs out, its bubble collapses and the interstellar medium reclaims the space. The magnetic fields and plasma flows of the galaxy fill the void, mixing with whatever remains. For massive stars, the process ends in a supernova, which sends new material into the interstellar medium, enriching it with heavier elements. Those elements eventually become part of the next generation of stars and planets. The edge of the heliosphere, then, is not just the boundary of the sun's influence, but a point along a continuous cycle of creation and dissolution that defines the life of galaxies. From a human perspective, the idea of crossing this boundary carries both scientific and symbolic weight. It represents the extension of our reach beyond the confines of one star's domain into the shared environment of the cosmos. When Voyager 1 passed the heliopause, it didn't just travel into interstellar space. It carried with it a message, a record of life on Earth, stored on a golden disk attached to its side. That record now drifts through the galaxy, a fragment of human origin moving among the dust and gas that connect all stars. In the quiet of interstellar space, it continues to travel, long after the instruments that sent it there have fallen silent. The interstellar frontier is not empty of future exploration. Missions have been proposed to follow the Voyagers, using newer technology to reach and study this boundary more directly. These interstellar probe concepts aim to travel faster and farther, mapping the outermost structures of the heliosphere, observing how it interacts with the galaxy, and perhaps even reaching the undisturbed interstellar medium within a human lifetime. Such missions would extend our understanding not only of the sun's influence, but of how stellar systems in general live within their galactic environments. At this frontier, every direction leads to something new. Behind lies the solar system, with its planets, dust and magnetic fields, all shaped by the sun's steady output. Ahead lies the galaxy, with its clouds, stars and spiral arms. The heliopause marks the transition between these scales, between local and galactic, between known and infinite. It's not a barrier, but a gradient, a reminder that the universe doesn't divide itself neatly into regions. It blends continuously from one environment into another. If you could drift far enough beyond, the sun would shrink into a bright dot, indistinguishable from countless others. Yet everything you had left behind, the planets, the light, the history, would still be tied to it by memory and motion. The boundary you crossed would remain invisible, but its existence would define the difference between where you came from and where you are. In that sense, the interstellar frontier is both a physical place and an idea, the point where a world becomes part of the wider universe. Silence in space is not the absence of sound, it is the absence of air to carry it. There are no molecules vibrating, no waves pressing against an eardrum, no echo returning from a nearby wall. Yet this silence is not empty. Between the planets, between stars, and even beyond the heliosphere, there are vibrations of a different kind, magnetic, electric, and energetic, that travel through the plasma filling space. They cannot be heard directly, but they exist everywhere, woven into the structure of the solar system. To listen to the silence of space is to listen to these hidden movements, to the patterns of energy that speak in a language of particles and fields rather than pressure and sound. On Earth, silence is simple to imagine. It is the stillness between noises, the pause before a voice begins or after it ends. In space, there is no such pause. There is only continuous motion at scales too small or too vast for the human ear. The solar wind carries waves of magnetic energy that rise and fall. Cosmic rays strike atoms, sending out brief bursts of charged particles. Even the background radiation of the universe itself hums faintly, with the residual energy of its origin. The silence of space is full of these signals, continuous and without rest. What we call silence is only what our senses cannot detect. Spacecraft, equipped with instruments that translate electromagnetic fluctuations into frequencies we can hear, reveal a world that is never still. When the Voyager probes recorded data from the plasma waves in the interstellar medium, scientists converted the information into sound. The result was not silence, but a slow, resonant tone, a rising and falling vibration that seemed to breathe. It wasn't a melody or a pattern, just the natural oscillation of charged particles moving through magnetic fields. The same process, when applied to data from near Earth or Jupiter or Saturn, produces a wide range of sounds, hisses, crackles, low hums, and rhythmic pulses. Each one is the voice of a different environment, a different set of conditions, a different interaction between energy and matter. These sounds are not sound in the traditional sense, but they give form to what would otherwise be invisible. They show that even the emptiest regions are alive with movement. The solar wind, though thin, is filled with waves. When it encounters the magnetic field of a planet, those waves reflect, refract, and change shape. The boundaries of magnetospheres and ionospheres are full of activity, each producing its own set of plasma oscillations. Scientists studying these vibrations can determine the density, temperature, and motion of space plasma from millions of kilometers away. The silence between planets is in fact a constant conversation carried in fields and frequencies. Closer to home, the Earth itself emits its own quiet chorus. The planet's magnetic field produces natural radio emissions known as chorus waves. These waves are generated by electrons spiraling along magnetic field lines, their motion amplified by interactions with the solar wind. When converted to sound, they resemble a distant chorus of birds at dawn, rising and falling in waves. These emissions are strongest in the morning hours and during periods of increased solar activity. They are part of the invisible rhythm that surrounds our world, unnoticed by human ears but constantly present. Every planet with a magnetic field produces its own version of these emissions. Jupiter's are especially powerful, driven by its immense magnetosphere and the motion of charged particles supplied by its volcanic moon, Io. The radio waves from Jupiter can be detected even from Earth using simple antennas. They vary with the planet's rotation, and the position of its moons, creating patterns that scientists use to study the dynamics of its magnetic field. Saturn's emissions are softer but equally intricate, modulated by interactions with its rings and moons. Even the smallest changes in particle density produce shifts in these signals, subtle signatures of the constant motion within the planet's environment. When sunlight strikes the upper atmospheres of planets, it generates ionization, creating thin layers of plasma that also produce their own sounds when translated from electromagnetic data. These layers respond to solar activity, brightening and fading, rising and falling in density. Spacecraft passing through them record fluctuations in electric potential, the signatures of invisible tides. Each world's silence carries a different tone, higher where the plasma is dense, lower where it is thin. Together they form a kind of symphony of energy, one that never ceases, even in darkness. In the space between planets, where the density of particles is lower, the sounds become slower, deeper, more diffuse. The solar wind expands and cools, carrying its embedded magnetic field outward like an unbroken thread. Fluctuations in that field propagate as waves, Alphen waves, named after the scientist who first described them. These waves carry energy and information, allowing disturbances near the Sun to influence regions far beyond the planets. When the Sun releases a burst of plasma during a flare or coronal mass ejection, those waves intensify, spreading outward in concentric ripples. Instruments detect them as variations in particle speed and magnetic direction. Translated into sound, they resemble long, distant rumbles, the solar system's version of thunder rolling across space. The silence of space also includes the background radiation that fills the universe. This cosmic microwave background is the leftover glow of the Big Bang, stretched and cooled over billions of years. Its frequency lies far below what the ear can detect, but it can be represented as a faint hiss. This background permeates every part of space, including the region between stars and galaxies. It is uniform in all directions, yet not perfectly so. Tiny variations in its intensity mark the seeds of structure, the differences that eventually led to galaxies, stars, and planets. In that sense, even the most ancient silence contains the memory of sound, the faint trace of the universe's earliest expansion. Listening to these signals is a way of understanding motion in the absence of touch. The data reveal that space is not static, not even in the regions that appear empty. It pulses with the flow of particles and the shifting of fields. The boundaries of the heliosphere vibrate as solar and interstellar pressures compete. The tails of comets hum with currents of charged dust. The magnetic fields of planets flicker with bursts of radio energy. Each signal represents a physical process, a transformation of energy that can be measured, mapped, and understood. To human perception, though, this environment remains silent. Space has no air, no medium for traditional sound waves. Astronauts orbiting Earth experience an eerie stillness. Outside the spacecraft, tools make no noise, collisions produce no clatter, and speech is confined to radio. The only sounds come through vibration transmitted by solid contact, the hum of machinery, the movement of air within the cabin, the rhythm of one's own breathing. This silence is both real and deceptive. It's the absence of one form of sound, but the presence of countless others in forms our senses can't perceive. The absence of air doesn't mean the absence of connection. Radio waves, a form of electromagnetic radiation, travel easily through space. They carry voices, data, and signals across billions of kilometers. When we speak to spacecraft like Voyager or New Horizons, the conversation takes place within this silent medium. A transmission leaves Earth, spreads outward through the solar system, and eventually reaches the craft hours later. The return signal, faint and delayed, carries information about places no human has ever seen. The space between those signals is empty of sound but full of meaning. Every transmission is an interruption in the silence, a reminder that even the void can be used for dialogue. The discipline of listening to the silence, of translating electromagnetic data into sound, has become an art as well as a science. The process known as sonification turns numbers into audible frequencies, allowing scientists to perceive patterns that might be missed visually. It's also a way to make the data intuitive, to let the ear detect relationships between waves, densities, and events. When plasma oscillations from the outer solar system are played as sound, the frequencies rise and fall with the density of the medium. When solar storms occur, the pitch changes abruptly. These transformations make it possible to hear the rhythm of space, to perceive the invisible activity that defines it. Instruments aboard spacecraft like Cassini, Juno, and the Parker Solar Probe have recorded the electromagnetic signatures of space near other planets and near the Sun itself. Cassini's flybys of Saturn and its moons revealed the sounds of plasma waves moving through the planet's magnetic field. During its descent into Saturn's atmosphere, the probe transmitted data that, when converted, produced a gradual deepening of tone, a sonic representation of its final moments. Juno's passage through Jupiter's radiation belts recorded bursts of energy so intense they sounded like static explosions. The Parker Solar Probe, flying through the outer corona of the Sun, has captured oscillations caused by turbulent magnetic waves, translating them into low, pulsing sounds that reflect the constant motion of the solar wind. Each of these recordings represents a form of silence made audible. They are not artificial, not added for effect, but direct translations of data into human scale. Listening to them gives a sense of the complexity hidden behind what appears to be emptiness. It's not a silence of absence, but of transformation, a silence that contains motion, energy, and structure too subtle to reach us directly. When you imagine space, you might think of a deep, motionless void, a place where nothing stirs. But in reality, it's closer to an ocean of invisible movement. Waves travel through plasma, particles collide, magnetic fields twist and reconnect. The scales are vast, the speed's immense, but the processes are constant. The solar system is filled with oscillations, from the smallest fluctuations in the solar wind to the largest resonances of planetary magnetospheres. Each one produces its own signature. Some last seconds, others endure for years. Together they form a continuous background, a quiet that is never truly still. There's also another kind of silence in space, one that comes not from the lack of sound, but from the distance itself. Signals fade as they travel. Every transmission weakens, every reflection grows dim. Even light, the fastest form of communication, takes time to move between worlds. The further away something is, the more delayed its voice becomes. This temporal silence, the gap between event and perception, is one of the defining qualities of the cosmos. When we observe a star, we're seeing it as it was years or centuries ago. When we listen to the data from Voyager, we're hearing the state of interstellar space as it was nearly a day before. Space is full of signals, but none of them arrive in real time. Silence is not emptiness, it's delay. This concept reshapes how we experience the universe. Everything is connected, but through intervals of time so vast that immediacy vanishes. The silence between signal and response, between cause and observation, becomes part of the fabric of understanding. In that way, space teaches patience. To study it is to accept that knowledge comes slowly, filtered through light years of distance. This silence is the medium through which time itself is revealed. Even within the human body, silence and vibration coexist. Our planet's magnetic field interacts with the solar wind, producing variations that can be detected at the surface as minute fluctuations. Sensitive instruments pick them up as geomagnetic pulsations, changes in frequency that can influence everything from power grids to atmospheric currents. Though inaudible, These pulses form part of the background of life on Earth. The same cosmic influences that create the auroras also shape the invisible rhythm of the planet's electromagnetic environment. The silence of space extends inward, touching everything, even when we can't feel it. Instruments that record gravitational waves, a different kind of vibration altogether, have also revealed that even space-time itself is not silent. Gravitational waves are distortions in the fabric of space caused by massive objects like merging black holes or neutron stars. They stretch and compress space as they pass, moving at the speed of light. When translated into sound, they produce faint chirps, quick rises and falls that mark the moments of cosmic collision. These signals are extraordinarily weak, requiring detectors of incredible sensitivity, yet they show that the universe resonates on every scale, from the smallest plasma fluctuations to the deepest gravitational motions. In that sense, silence is never absolute. What we call silence is only a limit of perception. Space is filled with vibrations, fields, and flows that continue regardless of whether anyone can hear them. Listening to the silence means expanding the idea of hearing to include all forms of detection: light, magnetism, radiation, gravity. It means recognizing that everything moves, everything oscillates, everything leaves a trace in the fabric of reality. If you were floating between the stars, far beyond the heliosphere, the silence would feel total. There would be no sound, no vibration your body could sense, no wind or surface to carry it. Yet your instruments would tell a different story. They would register plasma waves, magnetic pulses, cosmic rays striking sensors, the faint hiss of background radiation. Each of those readings would correspond to a sound if translated. The silence would be full of unspoken motion. Back near the inner solar system, even the smallest events produce similar effects. The passage of a meteor through Earth's atmosphere creates radio signals as air ionizes around it. The tail of a comet interacts with the solar wind, creating waves that propagate along magnetic field lines. The moon's surface, bombarded by micrometeoroids, sends out bursts of charged dust detectable by orbiting instruments. Every motion leaves its mark, every interaction generates a response. The silence between worlds is, in reality, a vast collection of these responses, subtle, continuous, and everywhere. What makes this silence compelling is that it exists at all scales. On a human scale, it's the quiet of the void. On a planetary scale, it's the interaction of magnetic fields and plasma. On a cosmic scale, it's the slow undulation of gravitational waves moving through space-time. The same principle governs all of them. Movement leaves vibration, and vibration carries information. The universe is full of it, though we perceive only a fraction. Listening to the silence then becomes a way of recognizing connection. The quiet between planets, between stars, between galaxies, is not a void, but a medium. Energy moves through it, linking distant places through invisible waves. Every signal we detect, every hum and fluctuation, is part of that ongoing conversation. The universe does not speak in words, but in oscillations, magnetic, electric, gravitational, all unfolding in the same vast silence that we once mistook for emptiness. And within that silence, the traces of our own presence travel too. Every signal we've sent, every transmission from a spacecraft, every echo of a radar pulse aimed at another world continues outward. They fade quickly, swallowed by the background noise of the galaxy, but for a time they remain, ripples moving through the same medium that carries the vibrations of the stars. To listen to the silence is also to listen for ourselves, to realize that our signals, however faint, are now part of the larger hum of the universe. Somewhere beyond the range of those signals, beyond the point where our instruments can still measure, the silence continues unchanged. It carries the faint resonance of cosmic rays, the low frequencies of plasma waves, the soft hiss of the universe's earliest light. And in that same medium, moving among those same vibrations, are the remnants of our machines, Voyager, Pioneer, New Horizons, still transmitting, still sending back the smallest hints of sound from the deep. They drift through the silence, not breaking it, but becoming part of it, their presence blending into the steady background of everything that moves between the stars. In all the silence that fills the space between planets, there is one kind of signal that did not originate from nature. It is faint, structured and deliberate. It travels outward through the same void that carries sunlight and cosmic rays, but it carries information not of physics, not of plasma or magnetism, but of thought. It is the sum of everything humanity has sent beyond its own world. The hum of radio transmissions, the voices of distant broadcasts, the commands sent to spacecraft, and the faint echoes that return. These signals are humanity's extension into the solar system, a slow, invisible thread connecting a small inhabited world to the wide and uninhabited expanse around it. When early radio engineers first began sending signals into the atmosphere, few imagined how far they would go. Radio waves spread outward at the speed of light, diffusing through space in every direction. Most fade into noise within a few light years, indistinguishable from the background radiation of the galaxy, but in principle, they continue forever. Each transmission, each word spoken into a microphone and broadcast to the sky, becomes part of the quiet static of the universe. The space between planets carries those signals just as it carries the sun's light. Even now there are faint echoes of human technology drifting far beyond the reach of their intended audience. Closer to home, the link between Earth and its spacecraft is maintained by a constant exchange of radio waves. Antennas on Earth send commands, and distant receivers aboard probes like Voyager, New Horizons and Perseverance respond with data. The Deep Space Network, a global system of large radio dishes, keeps this conversation alive. Signals leave Earth as bursts of electromagnetic energy, spread across billions of kilometers, and arrive hours later as faint whispers that must be amplified thousands of times before they can be read. Every image of another planet, every measurement from the edge of the solar system begins as a vibration in that invisible connection. This exchange defines humanity's physical presence in space more than any physical object. The probes themselves are tiny compared to the distances they cross, but the communication that links them back to Earth spans the solar system. That connection is part of what gives meaning to their journeys. Voyager 1, now in interstellar space, still transmits data that takes more than 22 hours to reach Earth. Each bit of information represents the crossing of billions of kilometers of silence, the persistence of a signal carried by the same electromagnetic laws that guide sunlight and radio waves alike. When we receive those signals, we are not just hearing from a machine. We are listening to the continuation of an idea that began here and reached beyond. For all our technological reach, though, the human connection to space is not purely mechanical. It is emotional and perceptual. From the earliest moments of consciousness, humanity has looked upward and tried to make sense of what lies beyond. The stars became markers of navigation, calendars for agriculture, symbols of stories, and metaphors for permanence. The planets, visible as wandering points of light, were among the first puzzles in the sky. Objects that moved differently from the stars and therefore seemed alive. For thousands of years, humans watched those motions without knowing their cause, tracing their paths with careful observation. Those records became the first language of astronomy, long before telescopes or spacecraft existed. That long history of observation built the foundation for understanding the solar system as a whole. When telescopes revealed that planets were worlds, not lights, the human perspective expanded dramatically. Each new discovery, moons orbiting Jupiter, rings encircling Saturn, polar caps on Mars, turned the distant into the tangible. The idea of space shifted from a backdrop to a place. Yet even as knowledge grew, the human experience of space remained one of distance and separation. The silence between worlds became a metaphor for both mystery and potential. Modern exploration has made that silence measurable. When a probe lands on Mars and sends back the sound of wind moving across the dust, or when microphones record vibrations on another planet's surface, the boundary between human and cosmic narrows slightly. The vibrations of those worlds are no longer just imagined, they can be heard and analysed. Instruments record pressure changes, measure dust particles, detect magnetic fluctuations. These are small steps toward bringing the unreachable into the realm of direct perception. Each signal that travels back through space is a link in the growing chain between humanity and the rest of the solar system. The human connection to the cosmos is not limited to machines or data, it's also biological. Every atom in the human body was once part of something older. Hydrogen, born in the Big Bang, carbon and oxygen forged in the cores of ancient stars, iron from the explosions of supernovae. The elements that make up a person are the same as those that make up planets, moons, and dust. The difference lies not in composition, but in arrangement. In that sense, humanity is not separate from the solar system, but a localized expression of it, assembled temporarily into form and consciousness. To look outward is, in a quiet way, to look inward at the matter that made us. This physical continuity is matched by a psychological one. The human brain evolved under the steady rhythm of sunlight and darkness, its cycles shaped by the rotation of a planet around a star. Circadian rhythms, the patterns of sleep and wakefulness, hunger and rest, are synchronized with the same light that defines day on Earth and glows across the solar system. Even when astronauts orbit the planet, their internal clocks still respond to that rhythm, adjusting to the repeated sunrise and sunset that occur every 90 minutes. The light that governs life on Earth is the same that defines the architecture of space between planets. As humanity reaches farther outward, that light becomes the only constant. The environments of space vary dramatically. Radiation levels, temperatures, magnetic conditions, but sunlight touches all of them. It powers spacecraft, illuminates surfaces, and defines the concept of direction. The side facing the sun is always the side of activity. The side facing away is the side of rest. The connection between light and awareness extends even here, linking human physiology with the behavior of machines and the nature of space itself. For those who have traveled beyond the atmosphere, the connection takes on a direct sensory form. Astronauts describe the sight of Earth from orbit as overwhelming, a single, self-contained world surrounded by blackness. The contrast between the vibrant colour of the planet and the depth of the surrounding void changes how they perceive scale and meaning. The experience, often called the overview effect, reshapes how they think about distance, isolation, and connection. From space, borders disappear, the thinness of the atmosphere becomes visible. The entire biosphere appears fragile, illuminated by the same sunlight that reaches all planets, but able to sustain life in only one known place. That perspective is part of the human connection to the solar system. To stand on Earth and look outward, or to orbit Earth and look back, is to see both sides of the same relationship, the inner and the outer, the source and the extension. Every image of another world, every signal received from beyond returns to this single point of reference. Space exploration is not just about distance, it's about reflection. The more we understand about what lies between planets, the more clearly we understand what it means to be on one. The process of reaching outward also changes our understanding of isolation. The silence between planets is immense, but it's filled with communication. Spacecraft speak to Earth. Satellites relay signals. Telescopes exchange data across continents. The network that supports exploration mirrors the structure of the solar system itself. Distributed, connected, and continuous. Each mission becomes a node in that network, a point where information flows between the human world and the cosmic one. This interconnectedness turns the void into something navigable. The silence, rather than separating, becomes a medium through which connection is maintained. When we send spacecraft to explore distant worlds, we send parts of ourselves, not just in the physical form of technology, but in the ideas those missions carry. The designs of the machines, the questions they are built to answer, the goals they pursue, all reflect human curiosity. The Voyager Golden Records, attached to both Voyager probes, carry sounds and images chosen to represent life on Earth. They were created with the awareness that they might never be found or understood, yet the act of sending them was itself meaningful. It was an acknowledgement that connection extends beyond expectation, that to exist in a universe filled with silence is to try to speak into it. Even now, the faint signals of those records travel through interstellar space, carried on spacecraft that have left the sun's domain. The recordings include greetings in multiple languages, music, and the sounds of nature. They also include a simple explanation of where the probes came from, encoded in diagrams that show the position of the sun relative to pulsars, celestial beacons scattered across the galaxy. The chances of anyone or anything ever finding and interpreting them are extremely small, but they serve a purpose that transcends probability. They demonstrate that awareness is not confined to one world. They mark the existence of a species capable of reflection, capable of understanding its place in the larger structure of things. The human connection to the cosmos is also measured through observation. The same light that travels between planets carries information that tells us about their composition, motion, and atmosphere. Every photon that reaches a telescope on Earth or in orbit has crossed millions of kilometers to arrive. When we study that light, we are participating in a dialogue that began with the sun and the planets themselves. Spectra reveal the presence of methane on Titan, carbon dioxide on Mars, ammonia on Jupiter. Polarized light shows the scattering of dust between worlds. In every wavelength, the universe speaks through its own structure, and humanity listens through instruments designed to translate those signals into understanding. This act of listening, of turning data into meaning, is part of what defines human connection. It's not simply about sending and receiving information, but about interpreting it. The raw signals from space are meaningless until they are understood in context, compared, and integrated into a broader picture. That process mirrors the way the human mind works, translating sensation into thought. The search for understanding beyond Earth is, in that sense, an extension of the same process that allows perception itself. The cosmos reflects our curiosity because we are products of it. In another way, connection also comes from vulnerability. Space is a reminder of how limited our existence is in both scale and stability. The thin atmosphere that protects Earth, the balance of radiation and temperature that allows life, the steady energy of the sun, all are conditions that could change. When spacecraft look back at Earth from great distances, what they see is a single, pale dot suspended in darkness. The famous photograph taken by Voyager 1 in 1990, known as the pale blue dot, captures that perspective. From nearly 6 billion kilometers away, Earth was just a point of scattered light, barely visible. Yet in that point lies everything human, every thought, every story, every sound ever made. The image is both humbling and connecting. It shows that scale does not diminish meaning. The connection between humanity and the cosmos also extends into the future. As technology advances, the possibility of humans traveling beyond Earth grows closer. The Moon, Mars, and eventually the outer planets are destinations that will one day host human presence, however temporary. Each step outward will depend on maintaining connection, communication, supply, and support. In a literal sense, life beyond Earth will rely on the ability to preserve links across distance. In a broader sense, it will represent the continuation of the same pattern that has defined exploration since its beginning, the desire to understand by reaching outward. When those future travelers look back toward Earth, They will see what astronauts already describe: the thin line between home and space, the faint glow of an atmosphere, the constant light of the sun reflected in oceans and clouds. They will carry with them not just equipment and knowledge, but the same questions that have driven exploration for centuries. Where do we come from? What connects us to the rest of the universe? What lies beyond what we can see? Each answer will reveal another layer of connection, another way the cosmos reflects itself through human awareness. Every step of exploration, from the earliest telescopic observation to the most distant spacecraft signal, has been part of a single unfolding relationship. Humanity is not an observer outside of nature, but a participant within it. The light that reveals the planets is the same light that powers the eye. The matter that builds spacecraft is the same matter that forms stars. The patterns of motion and gravity that shape the solar system also shape the chemical and physical structure of the body. The human connection is not metaphorical. It's literal, written into every atom and every force that exists. To listen to the silence of space is to listen to ourselves reflected through scale. To measure its boundaries is to measure our reach. To explore its distances is to explore our origins. The connection between humanity and the cosmos is constant and unbroken, even when distance seems infinite. Every signal, every photograph, every discovery is another thread woven into that vast network of exchange. It's not a network of technology alone, but of awareness. An understanding that what happens in the space between planets, between stars, between galaxies, is part of the same continuous system that gave rise to life on Earth. Somewhere in that continuity, in the faint hum of data returning from distant probes and the quiet observation of starlight through telescopes, humanity continues to extend its presence, not by dominating or conquering, but by perceiving. The act of noticing, of understanding, is itself a form of connection. And even as signals fade and machines fall silent, the relationship they established endures, because the knowledge they carried becomes part of the shared awareness that defines what it means to be human in a universe that is vast, silent, and full of motion. Between the planets, between the slow drift of dust and the long reach of magnetic fields, the solar system unfolds as both a place and an idea. It is the space that connects everything, the medium through which light, particles, and motion pass unceasingly. And within that continuity there is always a point of reference, a place from which all observation begins. For humanity, that place is Earth. Everything we have ever seen, measured, or imagined about the cosmos has been filtered through that single world. It is the anchor of our understanding and the starting point for every journey outward. Yet the more we learn about what lies beyond, the clearer it becomes that the boundaries between here and the rest of the universe are not barriers. They are gradients, zones of transition where one influence fades and another begins. The solar system itself is a continuous gradient of energy and matter. Closer to the sun, light dominates, driving motion and chemistry. Farther out, cold and gravity take precedence. Between these extremes, worlds orbit in balance, each tracing a path defined by the same underlying laws. Dust and gas move along those paths too, carried by solar wind and radiation pressure. Every object, from the smallest particle to the largest planet, is part of the same pattern, a network of motion that never stops. The distances are vast, but the principles remain simple. Energy flows outward, matter follows it, and everything is connected through gravity, magnetism, and time. What lies between planets is not emptiness, but continuity. Space is filled with the debris of creation, the breath of stars, the afterglow of processes that began long before the sun existed. The atoms that form the interplanetary medium have been elsewhere before, inside older stars, within ancient clouds, part of other systems. Their movement from one form to another is what gives the universe its texture. From the viewpoint of physics, there is no true isolation. Every motion affects another, every field interacts with others around it, every bit of matter experiences the pull of everything else. The universe is connected not by proximity but by influence. The space between planets also represents the boundary between human perception and the vastness that exceeds it. The distances involved are so great that they distort ordinary experience. Time and light merge into one measure. A message sent to a distant probe takes hours to arrive, and its reply requires another set of hours to return. Light from Neptune takes 4 hours to reach Earth, from the nearest star more than 4 years. To understand these scales requires abstraction, a step away from intuition and into comprehension that depends on mathematics and inference. Yet even in this abstract understanding, there is something profoundly human. The ability to conceive of such scales, to represent them in thought, is itself part of the connection that binds us to them. Every spacecraft travelling outward from Earth carries not only instruments, but also the capacity to extend human perception. Through them, we see regions that would otherwise remain invisible. Their sensors translate radiation, particles, and magnetic fields into data, and that data becomes understanding. Voyager's crossing into interstellar space was one of these extensions, a moment when the reach of human awareness expanded beyond the immediate influence of the Sun. The probe itself is tiny, but the concept it represents is immense. The ability of a species, bound to one planet, to reach intellectually and technologically across the limits of its natural environment. If you could stand somewhere far from the Sun, perhaps beyond the orbit of Pluto, and look inward, the solar system would appear as a faint disk of scattered light. The Sun would shine at the centre, and around it the planets would reflect varying shades of brightness. Venus white, Mars red, Jupiter and Saturn pale yellow, Neptune faint blue. Between them, countless grains of dust would shimmer, forming a soft glow. This glow, called the zodiacal light, is visible even from Earth under dark skies, a reminder of the dust and debris that fill the inner solar system. Beyond that, the scattered light fades into the blackness of interstellar space. But even there, the boundary is not abrupt. The particles of the solar wind continue, the influence of the Sun persists, and the quiet motion of gravity extends indefinitely. In that view, the space between planets becomes something tangible, not a void, but a structure of balance and exchange. Light moves through it continuously, carrying energy outward. Dust absorbs and re-emits that light as heat. Magnetic fields guide the movement of charged particles, shaping invisible currents. The result is a dynamic system in which every point, no matter how distant, participates in the larger whole. Space is not just the background against which planets move, it is the medium that sustains their relationships. Without it, the orbits, winds and cycles of motion that define the solar system would not exist. Humanity's understanding of this interconnected space continues to evolve. The instruments that measure it, spectrometers, magnetometers, detectors of charged particles, have revealed that interplanetary space is full of variation. The solar wind rises and falls in density and speed. Waves ripple through it, carrying information about solar activity. Dust particles collide, merge and fragment, maintaining a slow cycle of renewal. Even radiation levels change with time, shaped by the Sun's magnetic cycles. These observations show that what appears still is always changing, that even in the most remote regions, time is marked by fluctuation. The solar system's outer edge represents another kind of connection, one between the local and the galactic. The heliosphere, shaped by the solar wind, forms a boundary that protects the inner planets from much of the galaxy's radiation, but it also connects them indirectly to the broader environment. The interstellar medium that presses against the heliosphere is the same material that will, over immense spans of time, feed new generations of stars. This Sun, like every star, moves through that medium, exchanging energy and matter in subtle ways. Eventually, when it reaches the end of its life, it will return its own material to that same environment. The cycle that began with the collapse of an interstellar cloud will continue through that return. In this sense, the solar system is not a closed structure, but a phase in an ongoing process of transformation. Between here and forever, that transformation is the constant. Stars are born, shine, and die. Planets form, evolve, and erode. Dust drifts, collects, and disperses. On human timescales, these changes seem imperceptible, but over cosmic time, they are the essence of continuity. The space between planets carries the traces of these cycles, the radiation from dying stars, the dust from past collisions, the energy of moving magnetic fields. Every region of the solar system holds evidence of both history and motion. To study it is to study the flow of time itself, recorded not in seconds or years, but in the slow evolution of systems. The human presence in this system adds another layer to that record. For billions of years, the solar system evolved without observers. Its motions were indifferent, its interactions mechanical. But now one of its planets carries beings capable of reflecting on it, measuring it, and reaching beyond it. The awareness that arises from that reflection is itself a form of connection, a continuation of the same physical processes that created stars and planets, expressed through consciousness. The act of understanding space changes the meaning of space. It turns distance into relationship, isolation into awareness. When we speak of exploration, it's easy to think of it as expansion, of moving outward into the unknown. But it can also be seen as an inward process, a recognition of belonging. The solar system is not a separate environment. It is the context of everything we are. The same sunlight that warms Earth illuminates the moons of Jupiter and the rings of Saturn. The same magnetic fields that guide the solar wind reach into the orbits of distant comets. The same gravity that holds Earth to the Sun shapes the paths of every other world. To explore space is to explore the larger system of which humanity is already a part. Between here and forever, the balance of motion continues. The planets will circle the Sun for billions of years more, though their positions will change gradually as energy is exchanged between them. The Sun itself will age, brightening slowly as its internal reactions evolve. Eventually it will expand into a red giant, shedding its outer layers into space and leaving behind a dense, hot core, a white dwarf surrounded by the remnants of its former atmosphere. The material it releases will mix with the interstellar medium, contributing to the formation of new stars and planets. In that distant future, some of the atoms that were once part of Earth may become part of other worlds. The process is endless, driven by the same physical principles that govern everything between planets today. The human species, small and recent in comparison, has begun to participate in this continuity consciously. The spacecraft travelling beyond the solar system are extensions of that awareness. Each carries traces of the world it came from, data, symbols, and the physical materials of Earth itself. They are emissaries of a species learning to recognize its place within the larger structure of the universe. Whether they last for thousands or millions of years, their paths will continue long after their signals fade, moving through the same space that connects all things. From Earth, the night sky offers a view of that connection in every direction. The planets, moving slowly against the backdrop of stars, trace their orbits in patterns that have guided human observation since antiquity. Their light, reflected sunlight, carries the memory of the star that sustains them. The stars beyond, including the Sun itself, are part of a larger spiral of motion, the Milky Way turning silently in the dark, its arms filled with gas, dust, and light. The space between them is filled with the same kind of material that fills the space between planets, only thinner, older, more extended. The difference between here and there is only scale. The processes that shape one shape the other. If you could travel far beyond the Sun's influence, perhaps even beyond the nearest stars, and look back, you would see the solar system as a single point of light, indistinguishable from others. The details of planets, rings and dust would vanish. What would remain is the same as what is seen from afar: the glow of energy, the trace of motion, the quiet presence of gravity. From that perspective, the distinction between the solar system and the rest of the galaxy would fade. Everything would merge into the larger pattern of the universe. One structure within many, one moment within an unbroken continuum. Between here and forever lies that continuum, a chain of interactions that link the smallest particle to the larger structure. Every point of light in the sky is a reminder of it. Each one represents a star surrounded by its own system of planets, dust and space, each with its own boundaries and extensions. The distances between them seem immense, but they are connected through the same physical principles, the same cosmic fabric. Light from one system travels through the interstellar medium, passing through regions influenced by others, carrying information across the galaxy. That light eventually reaches other stars, other systems, other worlds, completing a cycle that has no true beginning or end. Humanity for now exists at one small point along that continuum. The exploration of space through instruments, observation, and imagination is a way of tracing that connection outward. The more we learn about what lies between planets, the more we recognize that it is not something separate from us. It is the environment that sustains motion, energy, and balance. The same silence that fills interplanetary space fills the atoms of our bodies. The same light that travels between planets is the light that enters our eyes. The same gravity that holds the moon in orbit shapes every step taken on Earth. To stand under the sky and look upward is to participate in that continuity. The light from distant planets and stars falls upon the same matter that once belonged to them, now part of us. The boundary between observer and observed dissolves in that recognition. Between here and forever, there is no true separation, only perspective. The spaces between worlds are not voids, but links, threads of motion and light that connect every part of existence to every other. And as the planets continue to move, as dust drifts and light travels, as signals fade and new ones begin, the solar system remains what it has always been, a field of connection. It is the space between that defines it, the quiet medium through which everything communicates. Between here and forever, the silence endures, not as absence, but as presence, filled with motion, memory, and the endless continuation of everything that has ever been.